We'll wait for. Okay. Okay, a very good morning, everyone. Welcome to our workshop. So this year, we're focusing on the trust aspect of federated learning in this workshop, which is in conjunction with FL-AAAI today. In the GatherTown virtual world, our workshop is located in room Blue 3. So if later on you wish to see the posters, please proceed to room Blue 3. The posters are outside the virtual room in GatherTown. Okay, so as Professor Yang mentioned just now, federated learning is in an upward trajectory in terms of the hype cycle about the technologies in data science and machine learning. And so far, it is still growing rapidly and attracting a lot of attention, both from the academia and the industry. For this year, for our workshop, we have received close to 50 submissions. And for each paper, we make sure that they receive at least 2 or 3 reviews from our reviewers. And in the end, we accepted 18 of them for oral presentation. And you can see the breakdown of submissions from all over the world that are accepted in the end. And we can see the US and China, they are playing a major role in terms of contributing to this topic. Well, a lot of other researchers from other nations are starting to join in as well. It's something very encouraging to see. For today, we have invited 5 exciting invited talks from leading researchers in this domain, both from the academia and the industry. We have Professor Dusi Niato from NTU, Professor He Bingsheng from NUS, Dr. Liu Lingjuan from Sony AI, who is also the sponsor of this workshop, Professor Tao Dacheng from JD, and also Nicholas Carlini from Google Brain. We have a strong lineup of invited talks today. And here I would like to acknowledge our program committee. We have a very strong, diverse program committee of reviewers to help us make sure the qualities of the submissions accepted to this workshop are very well. Thank you very much for the PC members. And we also want to thank the organizing committee led by Professor Yang Qiang. And this year, a lot of new friends are joining in terms of co-hosting this workshop. We have researchers from the Agency of Science and Technology and Research A-Star in Singapore, who have been playing a major role in terms of spearheading and organizing this workshop. Thank you very much. And also, one thing to point out is that the organization of this workshop is not the end of this journey in terms of working in this specific area in federated learning. We have organized a journal special issue in the IEEE transactions. Submission due date is still 1 month away. We're still waiting for more submissions, more papers from our workshop to be extended into the journal version to be submitted to this special issue. You can find the detailed information in our workshop website. Okay, so hopefully more people would decide to submit to this special issue. Okay, so I would also like to acknowledge our sponsor, Sony AI. It's a leading technology research company under a very major player in terms of technology development, which is Sony. So this year they have sent in a pre-recorded video about their company and the messages that they wish to send to our participants. So here I would start to play this video. Let me see. Okay.
だいまご紹介に預かりました飯塚でございます。コンピューターって言葉は非常にその誤解を招くんです。掛け算をやるとか割り算をやるとか足し算をやるとか、これはもっと広い意味でアーティフィシャルブレインといったような意味でのコンピューターを考えなきゃならないんですけども、そういうコンピューターというものの細胞といいますか、一つ一つのエレメントってものがその動かない形に変わりつつあるわけなんです。そういったその細胞全部が、セミコンダクターで置き換えられるということになって、そこにエレクトロニクスの進み方っていうのは非常に大きなものが期待されていると。それが世の中でそのもてはやされているということになるわけです。このアーティフィシャルブレインといったようなものが一体どういうふうな働きをしてくるだろうかと。例えば非常に交通っていうものが激しくなってまいりまして、人間が判断してステアリングをしてたりブレーキを踏んでたりしたんじゃ間に合わなくなってくる時代が早晩やってくるんじゃないかと。エレクトロニクスでやられるし、それから前の車との間は非常に距離の短いレーダーのようなものでその距離を測って自動的に速度の調整をやっていくといったように、人間の判断を使わずにこの車ってものを動かしていくってことが考えられるわけなんです。それは電子計算機のようなものが電子の医療センターっていうようなところに使われる日もそう遠いことじゃないんじゃないかと。その他ものを経営していくとか教育をしていくとかいうようなこともいいデータばっかりを蓄積して、そのデータの中から正しいものを選び出して次の推理を下していくというようなことは電子頭脳は非常に得意のところじゃないかと。人間の頭脳の働き、人間の大脳の働きなんてものは全然まだその生理学者医学者には分かっていないんで、これとそのエレクトロニクスと結びつけるなんてことはどうも到底夢にもできないっていうのが現状なんですけども、エレクトロニクスってものは好むと好まざるとにかかわらず、あらゆる社会にどんどんこれから入ってきて、相当人間の代わりの仕事もやっていくんじゃないかということを考えているわけです。
There's very few places where you can go out and say, I'm going to build an AI and I'm going to make it truly superhuman.
We're going to create artificial intelligence that will unleash the power of the human creativity and imagination.
Super exciting project. It's an amazing AI research and development activity.
또 비디오 게임 の中に再現したいなと思ったんですね。
Because of the realism of the game, it is actually very difficult to program agents.
We spent a lot of time trying to figure out what things we needed to change in order to get that superhuman performance.
Why are we building this GT Sophie agent?
This is not just a technical breakthrough project. It really is about bringing AI into the hands of the game developers who are going to build the new experiences for the players.
本当にすごいアグレッシブで、これからもっと一緒にレースしていきたいなっていうふうに思いましたね。
Imagine a vast world of gastronomy data at your fingertips. By developing groundbreaking AI, Sony AI will harness this data to inspire the artistic, iterative, and multidisciplinary recipe creation process. We want to use AI to complement your knowledge and experience to help delight your eaters. We are envisioning an AI-enabled application that will give you a variety of routes into every new creation. You might begin with specific ingredient in mind. AI can help you explore intriguing pairings based on a range of gastronomical data points. While pairing ingredients, you might want to adjust based on a range of attributes like texture and flavor profile. This allows you to refine your creative vision as you zero in on core ingredients for your dish. With your team, influence might come from anywhere. We're developing novel AI that takes abstract inputs like music, art, sound, color, and translates them into ingredients. Constraints in gastronomy are also We're growing the ability to tailor recipes to the eater. This lets us address areas beyond taste, like health, to build flexibility around dietary requirements, wellness, medicine, and nutritional impact. As well as tailoring dishes to the eater, understanding how what we create impacts the planet is a huge opportunity. With growing access to environmental data like carbon footprint, water usage, and seasonal and regional availability, we are more able than ever to pursue sustainable gastronomy. This will be an intelligent, interactive space to help unleash imagination and creativity around recipe design. Sony AI is drawing together data and insights from across the industry to empower chefs around the world and build the future of gastronomy with you.
We are interested in working with people that are eager to learn from others. We care about people. Like Sony is a company that cares about the artists and creators. And I think that's been the case throughout its history, and I think that's just the part of our DNA. Is a uniqueness to us, and it's our strength. I feel that's very important.
When we hire people for the organization, the things that I look for the most are people who are intelligent, work well in a team, and are highly creative. I find the team is most successful when people have the ability, when they run into a problem, to think of many ways to try to solve it, and then discuss and debate the merits of each direction, and then agree and go forward as a team in one of those directions.
So people, instead of working for the company, is working in the company with their missions and with their dreams. And that is definitely the train here that we need to capture. That makes us realize how important it is to provide an ideal workplace for the people to work here so that they can stay with us longer. People share the same values, share the same purpose, and that's the best way of collaborating.
Okay, I think that's all for the starting part of our workshop. And now we can move very exciting invited talks from leading researchers. So the first invited talk is by Professor Dusit Niato from Nanyang Technological University in Singapore. Niato is currently a professor in the School of Computer Science and Engineering at NTU. So he's a fellow of the IEEE. He received his Bachelor of Engineering from KMITL, Thailand in 1999, and PhD in Electrical and Computer Engineering from the University of Manitoba in Canada in 2008. His research interests are in the areas of Internet of Things, machine learning, and incentive mechanism design. May I invite Professor Niato?
Okay, good morning, good evening, everybody. So my name is Dusit Niato, and so the title of my talk today is Reliable Federated Learning for Mobile Network. Okay, so maybe I should share the screen, right?
Yes, yes. Professor, are you able to share? Okay. Yeah.
Can you see my screen?
Yes, yes, you can see. Yeah.
Okay.
Please.
So this is I am the professor at the School of Computer Science and Engineering, Nanyang Technological University. So this is the title of my talk, and this is the outline of my talk. So in this 20 minutes, right, talk here, so we are going to look at the federated learning and some security issue. How can we address the security issue by using the reputation mechanism? We are showing some detail of our schemes and present the numerical result and summary. So what is federated learning? This is just a quick recap. So the federated learning will enable machine learning engineers and scientists to work productively with decentralized data and privacy. So these are the two major features of the federated learning. So the idea is that we have the server, and the server typically they will do the machine learning training process by collecting the data from the user. But in the federated learning, it is different in the sense that the data will be kept at the user, but the server will distribute the model parameters to the user. The user use the data that they have and train the machine learning model, and then send the model back to the server, and then the server will aggregate the parameter updates for multiple users, and then build a global machine learning model for the applications. So this is the idea of the federated learning. Here we can see two major features: the decentralized, where the training and computation is done at the user, and the privacy, in the sense that data will not be transferred somewhere else. It will be kept at the user. So these are the two major features of the federated learning that help it to be more efficient and preserve the privacy. Now, given these two major features, there are still security challenges for the federated learning, and the typical attack for the machine learning is the poisoning attack. But the poisoning attack become much more complicated in the federated learning because the server has no ability to detect the poisoning pattern in the data, because typically in the centralized machine learning, the data will be collected from multiple sources into the server. So the server can run the algorithm, for example, anomaly detection, to detect whether the data is supposed to be the correct version or the genuine, the true data or not. But in federated learning, this challenge arise because the data will never be transferred to the server, and the server will have no way to detect whether the data is the true data or the fake or the poison data or not. So this makes the poisoning attack for the federated learning more challenging than the typical centralized machine learning. So the idea is of the poisoning attack is that we have multiple users, and some of the user may become poisoning user, trying to send the fake manipulated data, use the poisoning or manipulated data to train the machine learning model. And because the parameter trained by the poison data, it will be the wrong or inaccurate model parameter that will affect the performance of the global model. So for example, if we want to work on the recommendation system, some of the shops, right, may try to manipulate and say that some of the product has been sold more than the others. So that will give the influence to the global model that this is the popular product. So in this way, this user, this shop will manipulate the global model, and the recommendation result to the customer may say that this product, which is manipulated by the shop, is popular and you should pay attention, or you should be interested in buying that product. So this is how the poisoning attack happens. You see, if it is the centralized machine learning model, the server should be able to detect the anomaly why this shop can sell the certain product many more than the other shops. So this data can be used for the analysis. But the federated learning, we have no idea how to detect this anomaly. So there are some solutions for the federated learning to counter measure the poisoning attack. So we can see that if the malicious data owner is selected to be the worker to train the machine learning model in the decentralized fashion. So this worker, malicious worker, may intentionally launch and collude with the other worker to attack. Therefore, it is important to design a reliable worker selection for the federated. So that means we are not eliminating the data because the server has no access to the data. But what the server could do is to eliminate the malicious worker, so that only the reliable worker can participate in the federated learning machine training model. However, this problem cannot be solved in the traditional federated learning because there is no reliable and fair metrics to evaluate whether the worker is reliable or malicious. So majority of the federated learning system just randomly select the user to be the worker through some verifiable random function or the resource condition. However, existing schemes cannot measure the trustworthiness level of the worker so that it can remove unreliable and untrusted worker. So also there is no efficient and universal worker selection scheme. So it is difficult to design the selection scheme to identify high quality data contributor or the data owner to contribute to the federated learning. Moreover, there is no timely monitoring method for worker because it is hard for the server to monitor large-scale workers. Because in federated learning system, we may have hundreds or even thousands of workers contributing to the machine learning training process. So there is no efficient mechanism to maintain the to monitor the behavior of worker in a real-time fashion. As a result, malicious or unreliable worker may be selected to be the worker again and again for a new for the repeated federated learning task because of the lack of time accumulated matrix. So to address these challenges, we introduce a reliable matrix and design a reliable worker selection scheme for the federated learning. So the motivation is that we want to defend against a poisoning attack. So we design a reliable worker selection scheme for the model training, and the reputation is used to be the matrix to evaluate whether the worker is reliable or not. So this reputation is time accumulated matrix that can evolve and updated dynamically. So this is the idea that we adopt the multi-weight subjective logic model for the reputation, because in federated learning workers, there could be multiple factors that contribute to whether the worker is reliable or not. And in order to maintain the reputation information among the workers, we resort to the consortium blockchain to ensure that the reputation information of each worker cannot be manipulated by someone else. So this is our work related to the reputation-based worker selection scheme with consortium blockchain. So in this talk, due to the time limit, we are not going into the technical detail, but if you are interested in, please feel free to read our paper, which is Incentive Mechanism for Reliable Federated Learning, Joint Optimization Approach to Combining Reputation and Contract Theory. So this is the framework that we propose in our work. So we have three major components. The first one is the federated learning. The second one is the reputation blockchain. And the third one is the subjective logic reputation model. So for the federated learning training process, the first step is that the server or the task publisher will send the global model parameter to the worker. So the worker will use the local data set to train the global model parameter transfer from the server. So some of the worker here we could be reliable, but some of them could be malicious by manipulating the data set and train the global model. So the next step is all the reliable and malicious user will send the data or will send the parameter back to the server. So the server will evaluate the quality of the poisoning attack detection scheme. So in this way, they will also record the positive and negative result, whether the training is done properly or not. And then the server will generate the reputation opinion for the different worker, and the reputation will be uploaded to the blockchain. So in the blockchain, we have the worker or the different servers who involve the different workers. So the server or the task publisher will participate in this consortium blockchain to put in the reputation information of each worker. For example, we have this server. So the server will make a record that this user, the first user, produced quite relatively reliable model training model parameter. But the second user may not produce so good the result. So the task publisher will make a compute the reputation and trying to record into the blockchain by saying that the first user is relatively good by giving the high reputation score, while the second user have a lower reputation score. The other server will help to verify the reputation information from this server and put into the blockchain. Now, if the other server would like to use the data from the blockchain, they will retrieve the data from the blockchain and combine the data from the different servers recorded in this blockchain and compute the reputation by looking at the different parameters and trying to identify which worker should be the reliable worker and which worker will be the malicious worker. This result will be fed back to the server federated learning module. In the next round, the server may say that this user number 2 is malicious and it will be excluded from the model training process. So this is the repeated iterative process in the sense that the reputation will be recomputed, updated in the blockchain. The new worker selection decision is taken based on the data recorded in the blockchain and then used in the model training process. So this is the idea of our work. So we use the reputation calculation by using the subjective logic model. So this subjective logic model incorporates the opinion which denote the representation of the subjective belief, model positive, negative statement, and any other uncertainty. So these are the details of our multi-weighted subjective model. So we look at the different parameters from the different workers and the server. And the first step is we calculate the local reputation opinion. The second one is we integrate the recommended reputation opinion from the different server. And then we calculate the global reputation for the worker selection scheme to select the worker to participate in any federated learning process. So these are the major steps, and in the reputation, we use the interaction frequency to indicate whether the worker is reliable or not, how fast they respond to the training, and the quality of the model parameters updates that they transfer back to the server. This is why we incorporate 3 factors when we calculate the reputation, which is based on the multi-weight subjective logic. So again, we apply blockchain to record the reputation information, and this is the structure of the consortium blockchain. Again, we are not going into the technical detail, and these are the steps that I just explained. So we look at the numerical result, and we can see that given the poisoning attack strength and the randomness of the attack, we can see that when the attack happen more frequently with the stronger attack, so the model quality will drop. But given our federated learning selection scheme based on the reputation, we can see that we can still maintain the high quality or the accuracy of the model. And we make the comparison with the other scheme, and our scheme still perform better than the other scheme. So there are some future work to our scheme. We can employ the incentive mechanism based on the economics and pricing to be the motivation for the reliable workers to participate in the model training process. And we provide less incentive or reward to the unreliable workers. So in this way, we do not cut off totally, because we have uncertainty. We don't know exactly whether the worker is reliable or not, but we use incentive to motivate them to participate. And of course, we can reduce our cost. So the next future work is that the reputation management for the other reliable issue security attacks, such as backdoor attack and free riding, can be implemented. We can look at the federated transfer learning, and we can consider more general computing paradigm in addition to the federated learning, such as coded distributed computing. In fact, we have already extended this framework to the coded distributed computing. And if you are interested in, please feel free to access our recent work. Again, so this is the summary of my talk. And again, if you are interested in, please refer the technical detail in our paper. Thank you very much, and thank you for your attention.
Thank you very much, Professor Nyato. It's very
so
interesting
I make it on time.
Yeah, it's very interesting angle of organizing or managing the ecosystem of federated learning. So do we have any quick questions from the audience? Anyone wish to ask any questions? You can just unmute yourself and speak, or type into the chat. Okay. Okay, Professor Nyato, maybe I can ask one question.
Yes, please.
So in this model that you are working on, are there multiple federations for workers to choose from?
Yeah, that's correct. So there will be multiple servers working on the same group or similar group of the workers. So that's why, for example, one user can be recorded to be reliable or not reliable in the blockchain. And if the other server can refer to that behavior when they want to train their machine learning model parameters.
So is it possible for some workers to be colluding with some servers in order to boost their reputation?
Yeah, that could be, but because here we use the blockchain, only single server may not be able to influence the decision of the other server so much, because we already have a consortium blockchain, so that the server must be certified before joining the consortium blockchain. So that's one level of protection. The other one is that the other server will monitor each other in the blockchain. So that's help to verify and certify the reputation record in the blockchain.
Okay. Okay. Thank you very much, Professor Nyato.
Thank you very much.
Pleasure to have you.
Yeah. Okay, so I stopped the screen sharing. Yeah.
Sure. So the next invited talk will be from Professor He Bingsheng, who is the Dean's Chair, Associate Professor, and Vice Dean Research at the School of Computing in NUS. So previously he was a faculty member from NTU as well. industry as well as in the universities, and won many awards, served on many associate editorial boards for reputable journals as well as conferences. So he is an ACM distinguished member since 2020. So may I invite Professor He to share your screen?
Okay, can you see my screen?
Oh, yes, we can see.
Can you hear me?
Professor, please.
Can you hear me?
Yes.
Okay, great, thanks.
Thank you.
First of all, thanks for the invitation. Today, my topic is talk about how to build federated learning systems. So this is the big question we want to ask. So given the success of deep learning and all other machine learning systems, so we actually want to, the question fundamental we want to ask is that, can we build like TensorFlow, like PyTorch or scikit-learn for federated learning? So this is the main motivation of this talk, and also this is the journey we are doing now. This is the outline of my presentation. First, I will talk about the design principles. So we want to actually try to outline, we want to build a federated learning systems, and what are the design principles that we need to take care. And then we talk about our vision and a research roadmap. And then we talk about our ongoing work, including a tree-based system and the benchmark we have been doing, and also one-shot learning and so on. So, and then I conclude this talk. So actually, talk about the federated learning system. Actually, has its root in federated systems. So given, thanks to Duzit just now already present what is the federated learning, he gave a very nice introduction on this, so I will skip that part. But you see, actually, the interesting part is that if you look at federated learning system, actually it has the root at many federated systems, and even the federated system in the real world. Okay, we talk about the different country systems and so on, but here one of them is actually database system, and the other one is the federated cloud systems, and you see some of them in information retrieval, like federated search engines and so on. So in fact, federating system itself is not new. Okay, but what is interesting part of doing here is that we look at the analogy and the differences between different federated systems. And we find that actually there are many interesting things. The similarities here. The first one is, I think the main motivation of federation is because the participants have the heterogeneity. So either they are complementary or they have differences in their data sets, in their, if you talk about the cloud, they may have different price and so on and so on. So heterogeneity is definitely an essential factors in this kind of federated systems. And then the other one is the autonomy. So autonomy is that, so each participant has its own benefits and motivation, incentives to participate in this federation. I think it's just now, Duzit already mentioned about how to design incentive, how to avoid poisoning and so on. So this is actually related to this autonomy. But what are the major differences we find that? So beside the federation, like federated database and federated cloud, something is new here is that in federated learning, we are not just look at distributed learning system, we combine them, but also we need to take care of the privacy restrictions, because actually the main motivation of federated learning system is the data privacy. So that's why there may be some very interesting dimension to look at this. So, and federated learning system is quite, you can see actually learning system is going up very fast, and federated database and federated cloud is more or less like flat over the years, okay? And if you look at, okay, there is a survey we have written. So, and then if you are interested, you can read the details. But in general, we find that these 6 dimensions are very important to consider when you want to build a federated learning system. So including data partitioning, and I mean, basically how the data sets are partitioned, how the data sets are complementary with each other, and machine learning model, what kind of model will you support, whether tree-based, decision, or deep learning, and so on. And then how do you protect the privacy mechanism, and also how to support the communication architecture. So because by itself, federated systems are actually distributed. So they may have, if you talk about the enterprise, they may have dozens of participants. If you talk about like IoT, they may have thousands or even tens of thousands of participants. Or if you talk about mobile phone, you say mobile phone even can be even bigger, right? So then it goes to the scale of federation. Is like how we may have cross silo is in a small number of participants, cross device is basically a lot, okay? And then the motivation is very important. So that's why I think the motivation, Dusit had taught a lot. So now I don't want to go to details, but if you are interested, you can take a look at the survey. But the thing is, there are many interesting work there. So in fact, as I showed you just now in the Google Scholar, right, the number of publications goes up like almost more than exponentially in the past few years. So I think just like Prof. Yang Qiang just mentioned, I think federated learning has been growing very fast. Okay, so I think that is very, very interesting. So we have compared the related work in different dimensions. So and we find that these are very important the design factors along these 6 dimensions, and then we look at basically we need to care about the effectiveness, efficiency, and privacy and autonomy. So all this comes out actually we have different solutions. So we have different toolbox to an algorithm to actually leverage, no matter blockchain or even if you talk about just like if you talk about privacy, right? So privacy and security part, there are many things like TEE, trust execution environment, and blockchain and so on. They're actually, with each dimension, we have different mechanisms and tools and component that we can choose from. So that actually motivates us to actually, it is possible that we offer common abstractions to have a system, okay? So, and then there are some initial system nowadays like Google TensorFlow, Federated, PyShift, and so on, and Fate. And I think many of them actually are still in early stage. So, I mean, still a lot of work has to be done there because we have a lot of challenges because you look at these 6 dimensions, as I mentioned just now, there are many interesting research problems that is actually specific to federated learning. So I want to highlight maybe 1 or 2 here. It's actually very important. The first one I want to highlight is actually benchmark. I think given we have industry participant today, I actually want to advocate here that I think in terms of federated learning, we do need benchmarks for some real application scenario for federated learning. I know, so as you know, as academia, we actually try our best to build up some benchmark as I present later, but still we need some real applications, real data set, real scenario, so that we can actually drive the development of the system or algorithms, okay? And then the second point I want to highlight is that we shouldn't just look at the learning itself, we should actually go beyond that. So because data, so if you look at the whole data science or AI pipeline, learning is just a small part, okay, but it's important, okay? A small but important part of the entire process. So, but we should look at the entire cycle. So from the data creation, storage, use, and so on, till the day it actually destroyed, okay? So you can think about is like, I hope one day we have something like a federated learning system for data lake, for example. So that's something we still need a lot of effort there. So I hope to convince you this is, to build a system point of view, there are a lot of interesting stuff there. So in our research group, okay, so now I talk about our work. In our research group, we actually try to have built a system like something like a PyTorch and a TensorFlow. So over the years, we have recruit the students and also work with industry so that we can have more input from the federated learning system. So as you can see in this system, we really want to have the layer of abstractions. So from the interface, from the models, from the computation and the communication infrastructures, And then if you look at carefully about the party definition, is that we really want to have the common building block there. Is that we want to have the privacy mechanism as a self-contained building block there, okay? And then we build on top of like emerging hardware. As you know, my actual original expertise is on building system on this kind of emerging hardware. So I still find it's very useful in this context because training is very costly. And also sometimes we use the encryption method like a homomorphic encryption, actually it's also very costly. So I think put it all together is very important. And we are actually, we have putting step by step, but I think this one is basically what I'm saying here is that, so in fact, we need to work together to actually make it a more sustainable project. So we are actually in 1.0. So I think we are looking at benchmark, programming abstractions, and also we have built a tree-based systems. So this is really interesting part for me is that you can see we should have a bigger community here, not just the machine learning community, but you also need to work with the privacy and also the distributed system part. So it's really a drawing area, okay? So now I want to present some of our work, but I think due to the time, I really have to maybe just have a quick look about the research work here. Okay, so we have developed a tree-based federated learning system. Actually, it's open source. You can try to play with it. I will give you the URL later. And then, as I mentioned, benchmark is very important. So because we want to understand the algorithms, so we have two benchmark. One is OAuth. Basically, in OAuth, we try to assemble the real data sets. We want to create the scenarios from the real data set, public data set, so that actually people can download them and see how we actually can create federated learning scenario, no matter it's vertical learning or horizontal learning, so that we at least have some more realistic scenario to play with. And the second benchmark is actually, we talk about learner ID. Okay, as you know, in federated learning, as I mentioned just now, heterogeneity is important, but how to define the heterogeneity actually is, we call it learner ID. But learner ID actually have a lot of interesting dimension to look at. So what do I mean? What do we mean by learner ID? You can be in the data distribution in samples. It can be the feature in the features. It can be in the labels, or maybe a combination of them. So it actually, all this learner ID makes our system, make our algorithm very less robust. I mean, we actually have some papers look at it. In some scenarios, none of the algorithm works here. As actually all the algorithm works very badly. Okay, and then we have single shot algorithm so that we actually reduce the communication cost to the extreme. Okay, and then we talk about constructed learning and so on. But still today, I think I will just quickly go through some of them and show you some results. Okay, so as I mentioned just now, OAuth is really, we want to collect the public data set to create more realistic scenarios. So we actually try to design to cover different dimensions. And like I mentioned, the 6 dimensions just now, communication, privacy mechanism, and so on. So in the end, you can see if we compare the existing benchmark in machine learning or federated learning, actually we are more comprehensive in the sense. And this is the data set we actually collect. And then we actually have horizontal and vertical learning. So as you see, I give you one example why we think it's more realistic. For example, this we're trying to predict the age, right? So actually we collect the data from different sources. You can see actually it's the very different data set, and also there are others. So that's how we actually create more realistic federated learning scenarios. And also we do some analysis on it. So I skip this. Okay. So, but the thing is, I want to say the learner ID is very interesting. And also, I hope if you do experiments on federated learning, I do want you to actually follow what we have in the methodology here. Because it's, as you know, LangID can shift your learning a lot, right? So because all the federated averaging and so on, and fact plots and so on, many algorithms, they actually may work in one LangID scenario, but they may not work well in others. So we published one ICDE paper here. So I find this is very important. And in fact, we find, as I mentioned just now, none of the algorithms perform very well on some scenarios. So more work has to be done there, okay? So for more detail, I will leave it to you to read the paper. So about a tree-based system, as I mentioned just now, is open source. You can see the URL here. And the thing is, you can see what we are trying to do here is that more or less like a PyTorch is, we offer a lot of easy to use interface. We actually want to support Python, and so on. So, and then you can see we allow you to do deployment and features, and also we support horizontal, vertical, and hybrid. So all putting all together, we hope that we can support like something like GBDT, random forest, and so on, so that you can actually to play with it. So this is the system we are building now. But why we do GBDT actually is like it's very useful in many cases. I mean, deep learning is really useful in image processing and video and so on. But we actually find GBDT is really competitive in many other tasks. Like recently, we look at some financial applications. So GBDT is really good in the sense it has the training is very fast. The decision can be explainable and also predictable, something like that. So that's why you see there are many systems available like XGBoost, like LightGBM, CatBoost, and Standard GBM is our own system. Actually, it's also quite popular. We can see there are 600 stars in our GitHub. So it's really amazing. Okay, so the internal part of the GBDT is that so we actually try to have basically we look at the we develop an approach based on similarity on the record, on the instance, so that we can achieve the efficiency and accuracy and so on. So due to the time, I'm skip them, but I will refer you to read our paper. So basically, we based on similarity. So this is the pre-processing and training part of escape. And if we compare with the, okay, basically these figures compare with the different approach, like TFL is the state of the art. All in means you just consider all the data without privacy constraint. Solo is the individual parties. So you can see actually the CMFL is our approach. So it's very competitive, right? You look at errors or accuracy. So our approach has a lower error than much lower than the solo. So that's why we need to have federation. And is in some scenarios close to all in. That means close to you take all the data, right? So, but overall, I think it's reasonable, but there's some gap. We need to work more, okay? So the training is fast. Okay, I want to skip that. So we also have we have differential privacy for the tree-based system to address the model inference attack. So this is already been integrated into the fat tree system, as I mentioned. So for time being, I will skip that. So it's basically we need to have how to design the noise and in the tree level so that it can actually sanctify the bound. Okay, so I will skip them. But you can see the result is again on some result is quite competitive. So about one-shot learning is basically we use the logic transfer to achieve this one-shot learning. The basic idea is that basically we want to have the minimum communication between the parties, because in some applications actually the parties are not there for a long time. So that's why we want to design an approach that is only trained for once on the local party, and then they can share with, and then they can actually use for doing federated. Rather than doing federated, you have many iterations. So actually this motivates us another AI SG projects. Rather than doing federated learning in the data. We do federated learning on the models. So we actually envision there are many models in the future. So I think we are still, although it's one shot, but the performance is very competitive. So I will skip that. So in conclusion, we see that actually there are 6 design principles behind the federated learning system. So I show you how we actually address them in terms of GBDT and also factory systems. I believe this is very interesting journey towards some system like PyTorch or scikit-learn. Okay, so we have a lot of ongoing work. If you are interested in some of them, you can actually try to use our system, and also we are hiring. Okay, so I think I have to stop here. Thanks.
Thank you very much.
Everyone.
Thank you very much, Professor He. So I think the idea of moving forward for collaborating with models instead of just data is very intriguing. Could you share a bit more about this?
So our vision is this. Okay, so if you look at the history of the revolution in IT, okay, so I think 2 or 3 decades ago we talked about the program, the code is very important, and then 10 or 20 years ago we talked about data, we call it big data. Okay, so I think what we are looking at in the past, in the next 5 to 10 years, we envision that maybe it's the time for big models. Okay, so and you have seen that, right? So now people are actually very interested in pre-trained models. So we already see some of the trend moving towards that angle. So basic idea is that we want to give up on data. So what we see in the future is the model. So that is something we want to do in our AI SG project. But I think that this idea to me is very interesting in the sense, the model is what you learn from the data. And then this is the knowledge. But if you have a lot of models, how you actually combine the models together, right? So I think it's very interesting and fun. So, but of course, we still need the system like a PyTorch or TensorFlow to support this process. So that's why I'm working on this area.
Yeah, very exciting. Thank you very much, Professor He. It's great to have you here today. Thank you.
Thanks, everyone.
Okay, I think now we can move on to our first oral presentation session. Is Dr. Jin Chao here, our session chair?
Yeah, okay. Yes. Do we need a break or we continue?
I think we can continue in the interest of time. Yeah,
sure. Okay, so I think the first paper will be here, a margin-based federated adversary training approach. The authors are Chen Jie Zhang and Lin Juanlu from Zhejiang University and Solid AI. So yeah, now let's invite our speaker to present their paper.
Hello, could you hear me?
Yeah, yes, can hear you.
Okay. So could you see my screen?
Yes.
Okay, then I will start. Hello, everyone. I am Chen, a PhD candidate from Zhejiang University. Today, I want to present our work here, a margin-based federated adversarial training approach. This work is collaborated with Jie Zhang from Zhejiang University and Ying Juanlu from Sony AI. Federated learning, or FL, is a distributed learning system which offers a privacy-aware paradigm that allows to train a model using data from multiple sources without centralizing them. However, FL is vulnerable to well-crafted adversarial examples. During inference time, the attackers can add a very small perturbation to the test data, making the test data almost distinguishable from natural data, and yet classified incorrectly by the global model. So for example, in this figure, the attacker adds a very small perturbation to a panda image. So although the image is still a panda, but it's recognized as a given with high confidence by the model. So therefore, we need to train a model that is robust against adversarial attacks. In conventional machine learning, adversarial training, or AT, has been shown to be one of the most effective defense strategies against adversarial attacks. Previous studies proposed to apply AT to the local training of FL so as to improve the adversarial robustness of the global model. We call them Federated adversarial training, or FAT methods. A straightforward method is to directly conduct PGD on the local clients, which we term as naive FAT. However, FAT is more difficult than standard FL. In fact, FAT delivers a much slower convergence and lower natural accuracy than standard FL. FAT will become more challenging if the data are non-RID across the clients. One typical non-RID setting that commonly exists in real-world applications is the screwed label distribution. In this paper, we focus on the screwed label distribution setting. So in the right figure, we report the natural accuracy of standard FL, naive FAT, and our proposed gear on CIFAR-10 dataset, all with the non-RID setting. And naive FAT suffers from the training instability issue and has a much lower natural accuracy compared to standard FL and our method. We can argue that the low performance is due to that naive FAT fails to learn a good decision boundary. We summarize the challenges in learning the decision boundary in FAT. The first challenge is the statistical heterogeneity, where label screwness always exists in FL. The decision boundary is close to the data with minority classes, and thus has a much lower performance on minority classes. In the left figure, we show that performance of a learned local model in a random client. There is label screwness on this client, and the gray histogram demonstrates the training data size of each class. The performance of majority classes obviously outperform the minority classes. And the second challenge is due to that each client conduct AT. They use the most adversarial data to update the local model, which leads to a disordered decision boundary. As shown in the right figure, since the red triangles are the data of majority classes, the most adversarial data of the red triangle will cross over the decision boundary and locate at the area of blue circle. This adversarial data will push the decision boundary away from the red area and locate at the area of the blue circles, resulting in a very bad decision boundary and a low performance on the minority classes. So due to these two challenges, the global model is hard to provide good performance. To address the above challenges, we propose a novel FAT method called margin-based federated adversarial training, or GEAR. We focus on the local training of the clients, and the algorithm of the client's local update is shown in the right. First, GEAR generate the adversarial data and use the adversarial data for model updates. And GEAR encourages the minority classes to have larger margin and regularize the decision boundary to be smooth. To achieve this, we optimize the parameters with two new losses, a margin-based cross-entropy loss and a regularization loss. In the margin-based cross-entropy loss, we encourage a larger margin between the minority classes and the decision boundary in order to improve performance. In particular, we add a margin to the output of the ground truth class. So as shown in the equation on the top, MI YJ is the margin for the YJ's class on client I. And if the class YJ is the minority class, then its margin will be large. As for the regularization loss, we regularize the decision boundary by adding the L2 norm. We remark that by utilizing the above two loss functions, we can firstly increase the margin between the decision boundary and the minority classes. And secondly, we can smooth the decision boundary. As shown in the figure below, the decision boundary of gear is much smoother than naive FAT and can better separate the test data of the minority classes. Then we introduce the experimental setting. Our experiments are conducted on 3 data sets, CIFAR-10, CIFAR-100, and SVHN. We compare our method with 4 baselines. Before naive FAT, which was introduced just now, we also compare with FET-PGD, FET-TRITS, and FET-MART. We report the natural accuracy and the robust accuracy under FGSM, BIM, PGD20, CW, and AA. In the table above, we report the natural and robust accuracy across different data sets. And the figure below shows the learning curve of the different methods. As shown in these tables and figures, our proposed gear achieves the best performance, including the best natural accuracy and the best robustness on all data sets. Then we report the performance across different beta. Here, beta controls the levels, the label screwness. A smaller beta means more imbalanced labels. We also report the performance across different number of clients and different FL framework. And our proposed gear also achieved the best performance on all data sets. And to conclude, in this paper, we focus on the problem of adversarial robustness in FL and propose a novel margin-based federated adversarial training approach called GEAR. Our proposed GEAR can increase the margin between the training data of minority classes and the decision boundary by introducing a margin-based cross-entropy loss and regularize the decision boundary to be smooth by introducing a regularization loss, thus delivering a better decision boundary for the global model. And extensive experiments across various data sets validates the effectiveness of our proposed method. And that's all for my presentation. Thank you for listening. Is there any questions?
Yeah, thanks. Thanks for the presentation. Any question for the speaker? Or maybe I have a small question. So this can this method be applied to like different models and also like regression tasks?
Actually, that will be our future work, but in this work, we only apply it to the classification task.
Okay.
And as for different models, actually, it can be. You see in this figure, we showed the performance on different FL frameworks. Yeah.
Okay. Yeah. Okay. Thanks. Yeah. Okay. Now let's move to our second paper. So it's WP Shipley, efficient and effective incentive mechanism in federal learning for intelligent safety inspection. The authors are Chen Yiyang, Jia Liu, Hao Sun, and Tong Zhili and Zhen Xiangli from Digital Research Institute EN Group. Let's welcome our speaker for the presentation.
Hello, everyone.
Yeah.
As one of the biggest natural gas operator in China, EN Group's business has expanded to more than hundreds of cities, providing gas service for millions of families and thousands of enterprises. This paper focuses on household inspection on natural gas pipeline and device installation, as shown in Figure 1. Empowered by AI, there are several potential applications. However, the traditional solution cannot be continued to more and more regulations and the unfairness in the ecosystem, resulting in data silos among energy companies. In order to break the data silos, federated learning enables energy companies to train a super AI collaboratively. In addition, incentive mechanisms could be adopted to encourage energy companies with different data resources to collaborate in a fair manner. And the subject of this paper is about contribution evaluation. There are several comprehensive surveys on incentive mechanisms, and contribution evaluation is considered as a fundamental step. Shapti value is a classic and elegant solution in cooperative game theory. SV is proved to be the only solution that satisfies all four properties, which together can be considered as a fair contribution evaluation method. However, the time complexity of canonical SV algorithm is potential to participants' number. When adopting in FL, a huge amount of retraining and evaluating is introduced. Thus, canonical SV is infeasible. In academia, a collection of works have been donated to improving the efficiency of SV calculation. Typical approximation algorithm can be summarized as three types. There are gradient-based, sampling-based, and truncation-based approaches. Advanced algorithms utilize a combination of the above techniques, such as SOTA, GTG Shapley. Let's have a quick look for two alternative definitions. We think there is a link between combination and permutation. The synthesize are two. Regardless of the order of the participants in the combination S, its utility is equal. And the second, the proportion of a marginal contribution delta VI to SV is delta VI multiplied by the weight WS, which varies significantly with S. In essence, the truncation criteria in GTG Shapley treats each VI equally, which is contrary to the insights. Based on GTG Shapley and considering weight, we proposed WT Shapley. The complete procedural code of WT Shapley is listed in algorithm 1. And line 13 to 23 show weighted within round truncation operation, which are also the major difference from GTG Shapley. From the example, it clearly demonstrates the advantage of WT. In order to compare the performance of WT Shapley and GTG Shapley, experiments are carried out using many dataset divided and assigned to 10 FL participants in same and imbalanced distribution. The left upper and lower left subfigures respectively plot the error rate and the number of submodels with respect to the decreasing threshold, while the right subfigure reveals the trade-off between the number of submodels and accuracy. When the threshold decreases, the number of submodels increases and the error rate decreases. The difference between the area enclosed by the two polynomial fitting curve and the coordinate axis can be considered as the advantage of our proposed WT Shapley. And in table 2 takes a close look at the trade-off by revealing exact values in moderate situation. WT Shapley achieves better trade-off, and its advantage is especially significant in non-IID scenario. WT Shapley achieves an even lower error rate with about 1/5 to 1/2 number of some models of GTG Shapley. Real-world application results show that WT Shapley remains an advantage. The percentage of hazardous photos in city gas company C1, C2, and C3 increase in turn. As hazardous photos are more scarce, we built two validation datasets. The standard validation dataset contains small proportion of hazardous photos co-created by domain experts and data scientists, and the alternative is not. In the case of alternative validation dataset, the SV fails to reflect the proportion of hazardous photos. Hence, the standard validation dataset is essence and is essential and necessary for reflecting true business values. Based on our proposed WT Shapley, an effective end-to-end incentive mechanism is designed for natural gas household inspection application. Under our frame, a positive cycle can be derived, encouraging participants to provide more photos with potential hazards, achieving win-win situation among participants and model users within a vibrant ecosystem. The reported household safety inspection application was launched internally in ENN on June 30th of last year, with an average of 100,000 calls per day, with accuracy around 90%. With application feedback, the standard validation dataset is iteratively enriched and improved. Thus, the participants' contribution evaluated by WT Shapley always fits the real business value. In summary, we proposed WT Shapley and an efficient and effective end-to-end incentive mechanism and validated in real-world applications. In the future, we will continue to explore more efficient SV algorithms and continue to explore co-create intelligence in other scenarios in energy sector. And that's all. Thanks. Any questions?
Yeah, thanks Chen Yi for the presentation. Any questions for Chen Yi? If not, yeah, let's come to the third paper. The third paper is SSFL, tackling labor deficiency in feeder learning by personalized self-supervision. So the authors are Chaoyang He, Zhenyu Yang, Hiram Su, Mahdi Salman from University of Southern California. Yeah, let's welcome the speaker to present the paper.
Hi everyone, it's my honor to present our work SSFL here. So this is a joint work finished by FL-AAAI company and USC. So in this talk, I will introduce how to tackle labor deficiency in federated learning or personalized self-supervision. So the motivation of federated learning, I think in this workshop, we already talk a lot about privacy, but here I want to highlight that in practice, there are many scenarios about commercial interest and high communication costs that cannot do centralized training. So for example, here like commercial interest in drug discovery and some high communication costs in autonomous driving and the satellite setting. So there are three fundamental challenges in federated learning, including resource constrained Earth devices. For example, you want to train a very large model on Earth devices. Currently, it's very impossible because the state-of-the-art model in centralized setting already approach to billion level parameters. And the second challenge, we've already talked a lot about long ID, like system and data heterogeneity problem. So third challenge I think people really talk about is label deficiency. So you can imagine that in practice, there may not be enough label in Earth devices to do supervised training. That's because people may not have enough motivation to do it because it has a lot of privacy concern. For example, you will never label your private chat log or your photos taken with your family members. And also, even you provide a UI, maybe such UI designed very complex to make it compatible to different group of peoples. So in order to solve these three challenges in a single framework, in the past year in our group, we think a lot about how to have these three challenges being solved in a single framework. So we start from self-supervised learning. Actually, this is a very trending topic in machine learning community, especially in computer vision, like CVPR, UCC. People talk a lot about this self-supervised learning framework. Essentially, the idea is that we take a lot of raw image and do self-supervised learning as a pre-training task. After pre-training task, we have an encoder that's obtained from the pre-training, and then we can solely train a very thin classifier which does not have enough too many layers, and this downstream training may only cost a few iterations, so it saves a lot of cost for downstream tasks. People also call this self-supervised learning process as a fundamental development. So the secret of this self-supervised learning is that we have a dual neural network. The left side, we have an encoder. The right side, we have another encoder, which share the same architecture. And then we manipulate the image, which the process, we call it as augmentation. And for example, here you have a dog, you just flip it to another direction or change the color. And take this, and taking these two images, the encoder can train and obtain an output so the predictor can predict the label, the pseudo label for it. So in order to train the model, we construct a loss function, which we call the contrastable loss. So essentially the idea is that we calculate the similarity score between these two outputs, one from the predictor, another from the encoder. The idea here is that we try to minimize this loss because both of these two augmented image are from the same dog. So that's why we should minimize there to train the model. So on the right side, you can see that code is very, very clean, just a few lines of code. You can do self-supervised training. First, we have to data augmentation, and then we get some projector output and some hidden output, and then we calculate the loss. But here, you please be careful here that we do it a symmetrical way, meaning that we assume the predictor on the left side and also on the right side. So we have to calculate two distance, and then we update the model for both F and H, the predictor. So to understand this kind of framework in federated learning, we tried it in this SSL framework. Is a unified framework for self-supervised learning. So essentially the idea, we just replace the local SGD, which applies the labels to do the training with this client self-supervised learning optimizer. So by this optimizer, we don't need any labels to do local training. And surprisingly, on the right side, you can see the accuracy is almost the same as supervised learning. So this is the experience we tried in both non-ID and ID dataset in Scikit-learn. And this experience that motivates us further to think about how to solve these three challenges, how to overcome all the barriers in a single framework. I think the baseline experience is not enough because it does not consider any resource constraint and that's kind of data heterogeneity and system heterogeneity. So we are thinking about how to solve these two specific challenges from personalization and resource constraint perspective. For personalization, you can imagine that people already propose many famous framework like Perfect Me, Perfect Averaging Data, and some local adaptation. But the issue is that they may not fit for such a self-supervised framework. And the second issue is that if you look at the SYNSEM framework, the framework the dual network I just mentioned, actually requires a very large batch size. For example, the batch size may be 200, which may cost a lot of memory on smartphones and some early GPUs. So how to solve this challenge? We are thinking about to propose per SFL. So this is a personalized self-supervised learning framework for federated learning setting. So the idea is very simple. We just maintain dual models on each client. It contains a global model and the personalized model. And we only exchange the global model and keep the personalized model for each person. And then we calculate the regularization to get a conscience and personalization from each client. So the idea here is that we try to, so if you think from the centralized setting, the distance we just discussed is actually just try to minimize the two vectors. One is from the model, another one is the estimated value. So here we are further think about to enable the expected local representation like this eta and the H, big H, to minimize the distance between the global model and the personalized model. Essentially, it's local representation of any image and the global representation. So by this idea, essentially in the network on the right side, you can view it as we get a predictor output. We have another predictor output from the global model. We just try to minimize these two. And simultaneously, we think about how to do a balance, meaning that we have a lambda to correlate the relationship of the original self-supervised learning and the optimizer, like the regularization we just mentioned. So there's a lambda parameter that we can easily turn the distance between the local and the global model. So this is not a naive design, actually it's careful design and compare with some other options. For example, we can also think about, we can directly do local adaptation and the memo steps for the self-supervised learning, and also think about bilateral optimization. We do not minimize the distance, rather think about the weight. So I think these are three baselines we are compare with, and finally you find that our solution will be perform the best. So to first think about how to solve the system challenge like resource constraint, we have a further system design for personalized supervised learning on real devices. So this is a real system that you can run on Android smartphones and Azure GPUs. So in the algorithm layer, you can see here we have a SSFL trainer. It supports this 4 algorithms that I just introduced. And for the client side, we have a mobile SDK, which is not PyTorch or TensorFlow. We are developing a mobile neural network SDK to support such kind of training. So based on this algorithm and system design, we find that very promising result that you can see in a non-personalized way that we get a signal accuracy as centralized training. In a personalized manner, we compare this 4 algorithm and find our pink color is the per SSL performs the best. For some local adaptation, it may overfit in the later phase. For the green bilateral optimization, it cannot improve in the later phase. And for memo, it may also be overfit a little bit, but our framework can further improve the accuracy even in the later phase. So we also did some ablation study about to think about the memory constraint I just mentioned, how to solve the system challenge. Actually, if you want to train a very small batch size, actually the accuracy you can see is very, very low. So in order to solve this problem, we are thinking about gradient accumulation in our system design. So by this way, we can train a very large batch size, but use a minimum memory cost. So as you can see, the red color, we use a batch size for 200, but still get good accuracy. On the right side, we think about the line list. You can see even in some line list setting, we can still get good accuracy. So this ablation study and experience result prove that our framework can work in practice. So our future work contains 3 parts. I think this 3 part is very important to make this framework work well in practice. It includes how we can enable diverse AI applications. So just I only talk about computer vision. So how about natural language processing and drug discovery, for example, the graph mining. I think these are open problems. The second one is about how to run on realistic data sets. So in Federated community, everybody talk about it, but most of the research are done by using some fake Federated learning data set. I will have fake because it's just a synthetic data set by changing the partition from the centralized setting, for example, the pattern or some other data set just to change the distribution. I think that's not realistic. So I think to validate framework, we need such kind of thinking and benchmark. And the third part is also very promising that if you want to solve these three challenges in a single framework, to just think about machine learning is not enough. So we will think about machine learning and system co-design, and finally we have a unified framework. So that can lead to a maybe very good business model. Yeah, that's my talk. Any question?
Yeah, thanks, Chaoyang, for the presentation. Any questions for Chaoyang?
Yeah, you can email me if you are interested in this talk. Yeah.
Yeah, we can always like communicate offline.
Okay, thank you.
Yeah, so let's move to the fourth paper. It's partial model averaging in federated learning, performance guarantees and benefits. So authors are Sun Li, Antti, Chaoyang, and Simon Banster. So it's from University of Southern California and Amazon Alexa AI. So let's welcome the speaker to present the paper.
Do you see the screen?
Yes,
okay.
I can see now.
Hello, I'm Sonu Lee. Thank you for having me here today. Today I'm going to talk about partial model averaging in federated learning. This work is a collaboration with Amazon Alexa AI. So let's formally define the problem first. We consider the model aggregation scheme in federated learning. The core difference between the typical distributed learning and federated learning would be the model aggregation scheme. The left side figure shows how the models are averaged with two clients, the top and bottom, and the iteration goes from the left to the right. If the models are local solutions are averaged at every iteration, we typically call it synchronous SGD. And there's no model discrepancy across the clients because they are basically averaged at every iteration. On the right side figure, it's called, you may know well, Fed averaging. This is the foundational algorithm for federated learning. The core difference is we allow the local solutions to be updated independently and locally. So there should be the model discrepancy across the clients. So in larger scale federated learning, basically the variance of the stochastic gradients and the data heterogeneity across the clients make the local solutions move towards different directions on the primary space. This figure shows two examples. When you have two clients only, depending on the loss landscape, it's possible like these two local solutions are heading towards the opposite directions. But after a certain number of local updates, they are averaged, and this orange colored dot is somehow moving towards the red dot, the minimum, nearby minimum. But what if we have more clients? It's not always, but most likely they are moving toward all different directions. And the averaged model, this orange colored dot, would be moving towards the minimum more slowly. So this is the problem we consider in this work. So now we consider this specific aspect of the federated learning, when to aggregate the models. So in typical conventional federated learning algorithms, there is a strong assumption, like after a certain fixed number of local steps, all the local solutions are averaged at once. That is actually determined by a single hyperparameter, the number of local steps. So would it be the best way to aggregate the local solutions? So here's our solution, the partial model averaging scheme. We break the convention of periodic full averaging, and our main idea is let's synchronize a par model more frequently rather than just allowing fully independent local updates. This figure exactly shows the difference between the periodic averaging and our method. The left side, if we have two clients from U1, they will be attracted by different minimum because of this loss landscape, and then they will be averaged after these 3 steps. But in our case, after going to different directions, only 1 step, we average the model on 1 dimension. In this example, we have x-axis and y-axis. We can consider it like a 2-dimensional model. And we average these 2 guys on y-axis. So they are becoming closer, and then perform another local steps, and they will move towards different directions again. And this time we average them on x-axis, and they are becoming closer again on x-axis. And we do this interchangeably, x, y, so that we expect these 2 local solutions stay close to each other on the parameter space. This is the algorithm. It's kind of simple. Given k training iterations, instead of averaging the local solutions occasionally, we average of a certain distinct subset of the model parameters every iteration. So here's the empirical study on the impact of the proposed model aggregation scheme. The left side shows the impact on the model discrepancy. Here, model discrepancy means the actual distance between the local solutions. This is the first leftmost chart shows the comparison between the periodic averaging and proposed partial averaging. So as you can see, the periodic averaging, the model discrepancy goes up and down because we are periodically eliminating the discrepancy by fully averaging the models. The red curve is the discrepancy of the proposed method. Because we synchronize only a subset of the model frequently, it is not going up like the periodic averaging, but it also never goes to 0. After a certain number of iterations, the figure B, we can see that the partial averaging has a much smaller distance across the clients. And the right side 2 figures shows what happens on the local loss and the global loss. The blue curves are the global loss, the loss function computed from the global data sets. And the left periodic averaging, the blue curve sometimes sparks, like it spikes. It goes up sharply, and you can see a lot of spikes during the whole training, while the proposed method does not have it. It just goes smoothly along with the local loss. So here's the results, non-IID data results. It's unbalanced data generated using the Dirichlet's distribution, Cypher10, and IMDb review. Obviously, the proposed method shows faster convergence thanks to the suppressed model discrepancy. And the bottom side table shows the validation accuracy. In all cases, we have a bunch of different heterogeneous settings, like different Dirichlet's coefficients, different activation ratio. All cases, partial averaging works better, achieves the higher accuracy within the same number of training iterations. Right, so this is the work and insights. The most important lesson from this work was that more frequent partial synchronization can accelerate the convergence because the overall, the model discrepancy is not eliminated during the whole training. Our empirical study shows that it's okay. It somehow converges, guarantees the convergence. And the possible 2 future works, one is this work is actually the very extreme case where all the clients synchronize a part of the model every iteration. So, but in federated learning, all of you may know that the latency cost matters. It's not cheap. So could we make a kind of good practical trade-offs, like reduce the total number of synchronizations while we still suppress the model discrepancy across the clients? And that is one direction. And the other option is we were focusing on the general distributed optimization perspective only. But we know in modern deep neural networks, some components may have some different impact on the convergence. For example, attention for NLP tasks or residual connections for image processing. Could we consider such special connection patterns and their impact on the model discrepancy? So our second possible future work is architecture-specific model aggregation scheme. That's it. Thank you for listening. Any questions?
Thanks.
Hi, Dr. Lee. Sorry, I have a question. Very interesting talk. So when you are doing the partial averaging, so actually, which part are you gonna choose to average in each iteration? Do you have the criteria for that?
In this work, there's only one condition we follow. Given a certain length, given a certain number of local steps, we cover the entire model parameters at least once. And our theoretical analysis shown in the paper guarantees that the order does not matter. The order does not affect the convergence rate, which means you can actually choose whatever, any distinct subset of the parameters and average them one after another.
Okay, thank you.
Sure.
So yeah, I also have a question. So basically, can these techniques also applicable to like a traditional centralized training to improve?
Yeah, exactly. Yeah, actually, this idea itself was motivated from the centralized training, and yeah, it's applicable. We can just do the same thing, but that's actually the benefit would be different. The benefit would not be the acceleration of the convergence, but the communication cost, because basically in synchronous training we fully average the entire model parameters every iteration, but we can just view this technique like how to reduce the communication cost. We just synchronize a part of it every iteration instead of the full model, and we achieve kind of similar convergence properties like the synchronous training.
Okay, sure. Yeah, thanks. Thanks so for the presentation. Any other questions? Okay.
Thank you. I think you're muted.
Yeah, so let's move to our next paper. Next paper will be FIT-CV, a Federated Learning Framework for Diverse Computer Vision Tasks. It's from Chaoyang He and his co-authors. Let's welcome the speaker to present their paper.
Everyone, I'm come back again to present another paper. It's called FL-AAAI-22. Actually, it's a federated learning framework for diverse computer vision tasks. This is also joint work between FL-AAAI Company and the USC Research Net, and also some other researcher from HKBU, Tencent. So since this is not an algorithm paper, I mainly highlight some key features that how and what's the feature that our framework can provide. I think these are the three key challenges that I mentioned in the previous talk, including the resource constraint, data and system heterogeneity, and label deficiency. So in order to solve so many three challenges in a single framework, we in this paper, we especially talk about computer vision tasks. So if you look at current federated learning research, people mainly emphasize privacy, but never care about a lot of training tricks happens in computer vision domain. For example, this paper highlights that if we train ResNet with additional tricks, it can still achieve the state of that, can beat the state of that transformer models. For example, some tricks are never used in federated learning, including EMA, label smoothing, stochastic depths, a lot of others. So I think how to enable this in federated learning is a key challenges, especially in federated learning has been made it in a decentralized manner. So in this research, we want to tackle the problem that's to bridge the accuracy gap, because in federated learning domain, people just talk about privacy and using some naive optimizer and never think about these tricks. So the accuracy gap, as far as I know, is very big. For example, in Cyberturn, normally many federated learning papers just get the accuracy around 85, but in the state-of-the-art training, it can almost achieve 100%. So this is a research question that we want to ask. So in order to answer this question, we first build a framework called FedML. In FedML, in application layer, we provide diverse application, and CV is the first one that we think about. So in FedCV framework, there are multiple designs that enable computer vision in realist setting. So in communication layer, we think about RPC. Actually, we have another paper talk about how to do PyTorch-based RPC, which is tensor wireless communication. It can actually reduce the latency among different data centers. And also we enhance the framework using light square aggregation, which is the state-of-the-art square aggregation multi-party computation algorithm released by our lab in that paper published in this year MLCs. And in algorithm layer, we provide a bunch of algorithms that try to solve the three challenges independently or complementary. And we try to use a unified framework to make all these algorithms compatible. In FedCV, we especially think about different computer vision tasks, not just the image classification frequently used by optimizer researchers. We also think about image segmentation, object detection. So here, if you look at the right table, we provide models like DeepLab V3, UNet, and we also may provide some transformer-based image segmentation model later, and also including YOLO V5, which is a lightweight object detection model. So hopefully by plugging and play a method like this way, we can make this kind of model directly used by federated learning so that it can enable diverse applications like healthcare, smart home, and autonomous driving. So the backend of this CV framework is highlighted by this key design. Actually, if you look at the interface design, the left side is a traditional distributed training. We just look at it as MPI or reduced manner, meaning that we just load a batch of data and do forward propagation, get the loss, and then back propagation. And then we get gradient, and we synchronize gradient with other workers so that we get the aggregated gradient. But this is not programmable for federated learning because sometimes we have to customize the trainer to support diverse topology and different message passing. For example, you can define any kind of message to support different origin and all different payloads. So we make it work-oriented in FedML so that you can customize any kind of distributed training algorithm. And we also make this trainer customized to support computer vision. For example, here you can customize any kind of model architecture, and the code is very clean. You just have 4 lines of code, including topology configuration, load data, create model. And then if you want to customize the model, it's all loss function, especially those functions is very important for diverse applications, although they share the same backbone neural network. So to support this, we have a trainer and tester that you can define any kind of loss function as you like. So our aim at this framework is that to help you to write code once, meaning that you just define the same trainer, but every platform, including the simulation in a single machine or single GPU, or distributed training in multiple GPUs in a geo-distributed manner, meaning that different city want to train a model in a federated model, or you can still do it in smartphones and IoT devices. So every platform follow the same trainer so that we can enable programmers to have a paradigm that you can write once but run everywhere. So, here's some highlight feature that FedCV can enable diverse research, including a group knowledge transfer paper we published by our group, and some model and system dynamics core design and label deficiency. The SSFL paper I just mentioned is also developed based on this framework. And skew aggregation, we just manipulate a little bit of the function. We can enable these 4 algorithms together in a single framework. So for example, this one already introduced, and for neural net search, meaning that you can customize the local Federated trainer by using AutoML, meaning that you can search the model locally without needing to define the model architecture beforehand. And for skill aggregation, we can also customize the skill primitives, meaning that we also have primitives of the security API so that you can use it to support such kind of development research. And FL-CV also aims for mobile smartphones. For example, the Android smartphone, we are developing a framework that has a C++ engine. Hopefully, this is the ongoing work. Hopefully, we can share this to the entire community very soon. Finally, I want to emphasize that FL-CV is also supported by our Edge Cloud MLOps. This MLOps is developed by a startup. We are running this startup to support FL-CV in a zero code and no code platform. So next, I will introduce this in just 2 minutes. I think I can finish in 10 minutes. Yeah. So in this platform, you can find in open.fedml.ai. By this platform, meaning that you can combine any devices to this platform. For example, you can combine your Android smartphone by scan this QR code, then your device is online in this platform. And then you can invite your collaborators. For example, people in this group, in this workshop want to share and train a federated learning model. We just share the link to the Slack or Zoom chat. We can click this link and then we join the group. So once you join the group, you can create a group with your friends. For example, here we have a group like this way. And once you have a group, you can start training and share some experience out and check the accuracy. So here I just show you. So you can also check the demo tutorial in our FL-ML website. So here I just show you that when people already create groups. So in this tutorial, we have 4 people and they can create a group and do train a model. For example, we train a computation task. And after you start to run, you can select the device. For example, we have 4 devices. We can do a collaboration. And after this, we have a group. You can see the training status of this group, meaning that each smartphone may show you the status like initialization, training, stopping, or finish. For example, here, every device is training. And during the training, you can also see the loss. So everybody in this platform can see the loss for all the collaborators. And you can also observe the system performance. For example, how much memory are used in your smartphone and how much battery is cost. So by this way, we can do machine learning and system core design and core optimization. So essentially, this is the Edge Cloud platform that's supported by FedML. And so FedCV framework can fully use it. So the idea to enable FedCV to run in this Edge Cloud platform is that we maintain the library the same, but we ask the MLOps platform. MLOps is a web UI operating system that you can directly operate the library by using some command. So here we just call the command, but the command calling API, you do not write it. You just click the button and our system will launch the trainer. So that's the secret here. In FedCV, we will provide the experience out for image classification, segmentation, and object detection. So I think you can find the paper very easily. Just Google FedCV archive. You can find our paper and check more experiments out. So this is our FedCV framework. Any questions?
Thanks, Chaoyang. Any questions for Chaoyang?
Hi, Chaoyang. I have a question. A very interesting talk. So I see in the FedML's website, on the caption, it says that it's fair learning and analytics. So I was wondering that what are other analytics tasks you are like referring to or supporting now currently by this FedML framework? Thanks.
Yeah, this is a very great question. Actually, I think Professor He from NUS already talked a little bit about that that angle. So in his talk, he mentioned federated database. Right? Actually, federated database, if you think from MySQL perspective, you want to do Slack, start and query some data from your database and do some filter, right? Such kind of analysis is federated analysis in our mind. So means that it's not just learning, it's also about federated database. So that's what we need. But federated analysis is a little bit different from federated database that we first think about how to do a federated Spark. So UC Spark is a very famous framework in data center environment. We can build a cluster, a lot of CPU cluster to do some analysis, especially used for data pre-processing. After you process the data, you have a lot of feature, so you can train the model. So here, the same thing in federated learning. Without such pre-processing, you cannot train the model. So I think FA is more useful for data automation. So that's a ambitious goal in our startup that we hope the data pre-processing process can be automated so people can directly build a pipeline by plug and play. So we have FA first, and then we have federated ML first. We train the model, and then we got the model, and then we push the model to edge devices for inference, or just keep the model on the cloud. So I think that's the goal in our mind. So we are open to, so hopefully we can view this direction as federated data science. You can view that not just learning, a lot of analysis will be there. So a lot of opportunities, yeah.
Yeah, very interesting, thank you.
Thank you for your question.
Yeah, thanks. Any more questions? Okay, if not, let's go to the last paper for this session. Is presenting resilient feeder learning by gradient memorization. Is from Chen Chen, Lin Juanlu, Yu Chen Liu, Fang Zhao Wu, Chao Chao Chen, and Gang Chen. Is the authors from Zhejiang University, Solid AI, and MSRE China. So let's welcome the speaker to present the paper.
Hello.
Yeah,
yes, so I will begin. Hello everyone, I'm Yuchen Liu, a PhD candidate from Zhejiang University. Today I want to present our work, Byzantine Resilient Federated Learning via Gradient Memorization. And this work is collaborated with Chen Chen, Lin Zhuanlu, Fang Zhao Wu, Chao Chao Chen, and Gang Chen. So first, let me briefly introduce federated learning. Federated learning is a distributed learning system where the computation conducted parallelly on each participant and synchronized via exchanging gradients. In federated learning, each client has its own training data and only communicates gradients during training. Thus, the data never leaves local participants. It offers a privacy-aware paradigm, which allows the server to train a model using data from multiple sources without centralizing them. Over the past few years, federated learning has gained significant attention in a wide range of applications, such as computer vision, natural language processing, recommendation systems, and so on. As shown in the right figure, we can see that federated learning papers have skyrocketed over the past 5 years. However, in real-world applications, not all clients are benign, and there are Byzantine clients in the federated learning. So in federated learning, the server is not allowed to access clients' private data and therefore cannot directly monitor their behaviors. So as a result, federated learning is vulnerable to Byzantine attacks. A malicious party can easily create a small number of Byzantine clients to bias the model predictions. Different from the benign clients, Byzantine clients can upload well-crafted Byzantine gradients to poison the model, thus degrading the model utility. So therefore, it is important to develop a federated learning system that is robust against Byzantine attacks. And then I would like to introduce our problem definition. In a federated learning, benign clients always upload the gradients computed with their own datasets honestly, while Byzantine clients can upload arbitrary gradients to bias the model. We suppose Byzantine clients conduct untargeted attacks. That is, they aim to reduce the overall performance of the main task of federated learning. For example, to reduce the accuracy of classification tasks. To guarantee the applicability of these defenses, we consider a stronger attack scenario where the Byzantine clients have access to all benign gradients before conducting the attacks. Moreover, we assume that Byzantine clients may cooperate with each other. So most existing defense methods detect Byzantine attacks with one-round gradients. That is, the gradients of clients in the current round. In particular, after receiving the gradients from the clients, the server uses a filter function F to select the benign clients with one-round gradients. As shown in the equation, S sub B is the selected set of clients, and G sub M sub T is the gradient of the M's client in round T. So in such scenarios, Byzantine clients can upload well-crafted Byzantine gradients, which are between the smallest and the largest benign gradients. As a result, the Byzantine clients can compromise existing defenses and modify the optimal gradients. The main reason for the success of these attacks is that one-round benign gradients have a large variance, which leads to the failure of existing defenses. To address this issue, we propose a novel framework called average of gradients and shortened to AG, which utilizes the average of multi-round gradients to detect the Byzantine attacks. The algorithm is shown in the red rectangle in the right. After receiving the gradients from the clients, the server first averages the gradients for each client from the first round to the current round T. Then the server detects the Byzantine attacks with the average of the gradients, or we can call it multi-round gradients. Lastly, the server aggregates the gradients of clients in S sub B. Since our AG framework only changes the input of filter function F, it is a compatible approach that can be combined with most existing defenses by modifying the filter function F. We also provide theoretical guarantees for our proposed AG framework. In particular, we provide an upper bound for the expectation of the variance of multi-round gradients. Here, C sub 1, C sub 2 are constants. B is the batch size, and M is the number of clients. T is the communication rounds. So as T increases, the expectation of variance of multi-round gradients gets smaller. Therefore, the variance of one-round gradients has a higher upper bound, while the variance of multi-round gradients has a lower upper bound. Consequently, our AG framework can reduce the variance of benign gradients by utilizing the multi-round gradients and further improve the strength of the defenses. Then we introduce our experimental settings. Our experiments are conducted on 3 real-world data sets: MNIST, Fashion MNIST, and CIFAR-10. We adopt 2 attacks, following Empire and A Little Is Enough, which they are shortened to FE and LAAAI respectively. We consider 2 defenses as baseline, multi-chrome and oral. We further modify multi-chrome and oral into their AG version, that is AG multi-chrome and AG oral, and we compare them with the original multi-chrome and oral. The table shows the accuracy of different defenses under FE attack on FMNIST, and CIFAR-10 datasets. The figures show the accuracy of different defenses under lie attack on CIFAR-10 dataset. All the results show that our AG framework generally outperforms all the original version of the defenses. More experimental results can be found in our paper. So to summarize, in this paper, we show that existing defenses cannot well defend against by Byzantine attacks due to the high variance of one-round gradients. To address this problem, we propose a novel framework called AG, which is shortened for average of gradients, which utilize multi-round gradients to detect Byzantine attacks. And we theoretically show that our AG framework can reduce the variance of benign gradients and lead to a better defense performance against Byzantine attacks. Empirical studies on 3 real-world data sets justify the efficacy of our AG framework. And that's all for my presentation. Thank you for listening. So any questions?
Thanks, Yuchen. Any questions for Yuchen? Okay, if not, yeah, let's end of the first session. Later, we can continue with the second session.
Okay, thank you very much, Dr. Jin Chao, for hosting our session. And now we continue with our invited talks. So for the next invited talk, we have Dr. Lingjuan Liu from Sony AI. So Dr. Lingjuan Liu is a senior research scientist and team leader at Sony AI. Her current research interests span distributed and federated learning, privacy, robustness, fairness, and edge intelligence. Her work was supported by an IBM PhD fellowship and an Australian National University Translational Fellowship, and so on. She obtained her PhD from the University of Melbourne, and her works have received best paper awards from top conferences. Dr. Liu, are you ready to share your screen?
Oh, yes. Thanks for the introduction, Professor Liu. So can you see my screen?
Yes, yes. So
okay.
Good, please.
Okay. Let me get started. Hi, everyone. So I'm Lingjuan from Sony AI. So the title of today's talk is Towards Building a Private, Robust, and Fair Federated Learning System. As you can see from this title, so today my talk will mainly focus on 3 components in federated learning: privacy, robustness, and fairness. Those 3 components are also very important towards realizing building a trustworthy federated learning system. Before delving into each topic in more detail, let's first get started with a brief background of federated learning. As we all know, federated learning is a distributed learning paradigm. And due to this distributed property, actually federated learning opens new attack surfaces to both the malicious server and the malicious participant. The potential adversaries can infer sensitive information from the victim participant and also poison either the data or the model to compromise the model integrity. Let's next turn to the privacy part. And in fact, from the shared local model parameters or from the snapshots between the model parameters, actually the malicious participant can infer lots of sensitive information, including but not limited to the class representative, record membership, properties, sensitive attributes, even the training inputs and labels. You may wonder, okay, why the federated learning is still vulnerable to the privacy leakages, as all the participants, they actually share their learning parameters rather than the original training data. Actually, this is because the learning model is based on the original training data, and the learning model can be deemed as a high-level statistic of the data it was trained on. And the most recent research also demonstrated that even the model predictions can reveal training data privacy through the black box attacks. Therefore, no matter the original training data, the learned model parameters or updates or model scores or predictions should not be shared without any privacy protection. Next, I want to highlight that different federated learning systems may face different privacy leakages. And federated learning systems, the categorization method can be various. You can refer to our survey paper collaborated with Professor Yu Hang and Yang Qiang called the Privacy and Robustness in Federated Learning, Attacks and Defense. So in this survey, we have categorized federated learning according to the for example, for the cross-silo and cross-device federated learning, so this categorization is based on the number of the participants, the participancy frequency, the capabilities of the participants. Actually, the attacks that may work in the cross-silo settings may mostly fail in the cross-device settings because, as I said, the capabilities, the participancy frequency, and the number of participants, they are quite different. Similarly, according to the data and the feature distributions, so federated learning can be categorized as horizontal, vertical, and federated transfer learning. Also, those different federated learning systems face different privacy leakages. Similar story also applies to the different architecture for the federated learning, such as homogeneous federated learning and heterogeneous federated learning. Because in those two federated learning frameworks, so they share different information with parameter server. In terms of the privacy preservation, actually most of the previous privacy preserving mechanisms are motivated by the following privacy preserving techniques, including but not limited to the anonymity-based technique, the secure multi-party computation-based technique, TEE, differential privacy, quantization, or adversarial training-based methods. However, it should be noted that in practice, when we apply these privacy preserving techniques into industry, so the below KPIs should be considered, such as the computation communication cost, system capability, efficiency, and the trade-off between the privacy and the accuracy. Let's next turn to the second topic, robustness. Different from data privacy, robustness is more like system level. So the attacker in the federated learning system aims to poison either the training data or the learned model parameters to compromise the global model integrity in either a targeted manner or the targeted manner. For example, in the untargeted Byzantine attacks, so the Byzantine attackers can upload arbitrary values to the parameter server. Thus, the learned global model will be distorted and make mistake in an arbitrary manner as well. Similarly, for the targeted backdoor attacks, so the attackers can insert either the pixel-based or the feature-based or the whole image-based backdoor patterns to mislead the model to make mistake towards a target class. And also in the targeted civil attacks, so the malicious attacker can simulate multiple dummy participants and also control several compromised participants to launch a series of attacks towards a specific malicious objective, such as the label flipping attack. In terms of the robustness attack defense mechanisms, so previous works have tried the clustering-based technique, Euclidean distance-based technique, and the statistical-based technique, such as the median, mean, or the computation similarity-based mechanism. And also, some recent works also tried the non-bounding differential privacy, pruning, clipping, and smoothing-based techniques. However, it should be noted that Currently, there is no algorithm that can handle all kinds of above-mentioned robustness attacks, including the Byzantine backdoor or simple attacks. And there is always a conflict between the privacy and the robustness. This is because defending against robustness attacks usually requires the complete control of either the training process or monitoring the training data, which may inherently compromise the privacy. Our team also have done several works against the backdoor attacks. You can refer to our iClear and UIPS paper last year, and in our survey paper collaborated with Professor Yu Han and Yang Qiang. So you can find more answers in terms of either the privacy and the robustness defense and attacks. Another point I want to highlight is that there is always a gap between the academic attacks and the industry. The most recent work from the IEEE SP paper has pointed that actually most of the previous poisoning attacks may have no impact or may become completely ineffective against the production cross-device or cross-silo federated learning. And the exceptional cross-silo scenarios might be the financial domain with a very strong incentive. So if you are interested in exploring the gaps between those academic attacks and the industry, you can refer to this SP paper. And also we mentioned this point in our updated survey paper. And as you may see, actually most of the research on the robustness still focuses on the training phase. Actually, the test phase robustness against the different adversary examples is also very important in federated learning. This is similar as centralized learning. We want to build a robust global model in federated learning as well. So at the beginning of today's workshop, so our intern Chen Chen has presented a work titled GALE, margin-based federated adversary training approach. So this work also addressed the test phase robustness in federated learning. So you can refer to our paper to find how we solved this test phase robustness against different kinds of adversary examples in federated learning. So the last part of my talk is about the fairness. As you know, fairness is a very broad topic. And broadly, fairness can be categorized into the following three concepts: the performance fairness, collaboration fairness, and the ethical fairness. In KDD, last year, there is one tutorial called Towards Fair Federated Learning. So they also categorize the fairness into the following three concepts. Let's first get started with the performance fairness. So the performance fairness aims to encourage a more uniform accuracy distribution across the participants. And this concept is especially important for the wireless networks. For example, the connection to the internet. So the devices, they may have a different wireless connection quality. And in that scenarios, the federated learning wants to ensure the accuracies, the models distributed to those different devices. They can ensure the uniform accuracy distribution across the different end devices. The second important concept is called collaborative fairness or collaboration fairness, which is extremely important for the to sustain federated ecosystem. This is because, as we all know, the participants, especially in the cross-silo settings, different participants, they may contribute differently to the global model learning because different participants, they may all different numbers, and also their training data might differ a lot, and also their communication bandwidth, their computation power, and also they may face different security attacks. And the goal of the collaboration fairness is to ensure that the participants with higher contributions can receive higher rewards or the incentives. So the example here, I give two examples. One example is the federated learning across different competing companies, such as tech games and also the hospitals, and even the business units across a company. So our team and also Professor Yu Hang from NTU, so they have already devoted a lot in this area. So if you are interested in this area, feel free to look at the listed sample works here. And for the collaborative fairness, as I mentioned, so the goal is we want to ensure the participants with higher contribution to receive the higher rewards or the incentive. Two natural question is how to evaluate the contributions, how to quantify the contributions from the participants, and how to reward those participants accordingly. So let's first discuss about the contribution evaluation methods. So for this part, so there are normally three methods here. One is the naive evaluation-based methods, such as based on the data quantity and data diversity and the participants frequency, such as the communication rounds. The second one is marginal utility-based measures, such as the individual contribution evaluation in one-out methods, and the game theory-based methods, such as the separate value. And the third one is called mutual evaluation-based methods, such as let all the participants, so they conduct a pairwise measurement. So in terms of the rewards to the participants, the rewards could be also various. For example, the rewards could be the model-based rewards. For example, we can reward personalized models to different participants. We can also reward the more accurate models to the participant with higher contributions. And the rewards can also be the monetary incentive. The rewards could be also the computation power or resources, could be also the reputation, etc. And for the summary of the contribution collaborative fairness, actually collaborative fairness is interdisciplinary direction. It may cover the data evaluation, data market, and also the game theory community together. And however, there are also some open problems here. For example, how to quantify and how to allocate the rewards in the vertical federated learning, and how to design the efficient and effective incentive mechanisms in federated learning. And yeah, there may also other potential contribution measurement and reward mechanisms there, which is worthwhile to explore in the near future. So the last part is called ethical fairness. People may hear about this kind of fairness many times before. So this fairness is actually, we want to ensure that the federated trained models has no discrimination against some specific individuals, such as the female, minorities, disabled people, or the Black people. And the fairness, ethical fairness could be the individual fairness or the group fairness. And ethical fairness is especially important when the companies they want to deploy their models in the advertisement, credit application, employment, education, and criminal justice scenarios. For the ethical fairness, actually both the horizontal federated learning and the vertical federated learning. So there is an interesting conflict between the accurate measuring the model fairness and in terms of the data privacy protection. So this is because to accurately evaluate the model fairness always requires access to the data of all the parties. However, the federated learning forbids the access to the private data of all parties. Similarly, both the horizontal federated learning and vertical federated learning. So those two federated learning paradigms also face different challenges against the ethical fairness. So last but not least, so for the fairness part, so you guys can refer to the TDD 2021 tutorial, and also Professor Yang Qiang has a new book published by the Springer Nature last year, titled Federated Learning, Privacy and Incentive. There are many interesting points there. And yeah, so the last slide, I want to bring the relationship between federated learning and the privacy laws of different countries, such as the GDPR, to your attention. It's worthwhile to think about whether federated learning can be implemented, can be deployed in reality, whether federated learning is a privacy compliant learning system. For example, in the GDPR, whether federated learning can satisfy all the GDPR principles and can preserve the rights of the customers in the law. It's worthwhile to explore. And yeah, finally, so I want to announce that Sony AI is hiring research scientists, software engineers, and interns. So you can have a look at the special website at the FL-AAAI 2022 here, or either you can scan this QR code to apply, to drop your application on our official website directly. And thanks. Any questions?
Thank you very much, Dr. Liu. Any questions from the audience?
Sorry, I have a question.
Okay, sure.
First, thank you very much, Dr. Liu. And I have read your paper, Privacy and Robustness in Federated Learning, and it is very helpful for my research. My first question is that in the backdoor attack, you say that the backdoor attack should not significantly change the prediction outcome of other classes. And may I know how can we really define the significant change? It means that we measure the global model after aggregation to say that the job of other classes will not be high, and can we quantify the significant change?
Oh, okay, that's a good question. So indeed, as you know, because the backdoor attack is a targeted attack, so you can either empirically demonstrate that after you deploy some backdoor defense mechanisms, so the global model, the performance on the other benign classes, the performance will not be degraded too much, or either you can do the certified robustness against the backdoor attacks. It could be done in both ways, both either theoretical or the empirical.
Okay, thank you. And my second question is that in your paper, I have seen that you have surveyed some Byzantine attack. I have question on some other untargeted attack, whose goal is that they want to decrease the global model accuracy. And and I think this is different from the targeted attack, which the goal is to make the targeted accuracy to be high. So in this sense, we want to make the global model accuracy to be low. So to make it low, is there any possible theoretical support as a guarantee for this type of attack?
Oh, okay. I got your meaning now. Okay.
Thank you.
Thanks for your question first. So indeed, the untargeted attacks could be various. So the byte attacks is one type of the untargeted attacks. As you know, there are actually a lot of the evaluation metrics there. So one example is you can evaluate the accuracy, right? So the accuracy ranges between 0 to 100%, right? So in an idle case, so the attackers, they may want to degrade, they may mislead the learned models to make mistake on all the classes, which means the accuracy in the worst case would degrade to 0%, right? But in reality, there are few works that can degrade the learned models to be entirely useless. It's very hard to get, but you can do this actually also in both ways. You can do maybe the theoretical analysis. Maybe there is a higher bound of the after you launch those untargeted attacks, right? So higher bound means the model at most will reach this kind of the accuracy, right? This is from the theoretical perspective. Empirically, so you can launch different untargeted attacks to see how the model, how the performance will degrade.
Yes, and I understand what you mean, and thank you. First is that for the decrease of the accuracy, it is somehow like attack success rate, right? So that's the difference. And I want to know, to derive a theoretical bound, is there some possible theory for us as a guideline? For a yes.
That's a very great question. To be honest, I also didn't see a lot of works investigating the theoretical upper bound for the untargeted attacks. But I think it might be possible in the near future.
Okay, thank you. And my last question is that I saw your slides in the last or somehow. So I think there is also a right called the right to be forget. May I know if it's also related to federated learning for law? The right.
Yes. Thanks for your question. This is also a very great question. So the right to be forgotten is one GDPR principles and the rights of our customers. So also the Chinese privacy laws also regulates this right to the Chinese citizens. There are already several works that investigates the rights to be forgotten, how to make federated learning to unlearn those customers so who request their data to be forgotten from either the stored data storage or from the learned models. There are already several works there.
Oh, so maybe I need to search federated unlearning, right?
Yes. You can
Thank
find
you very
several
much.
works in the recent already NUIPS and ICML has 2 or 3 published papers in terms of the federated unlearning.
Okay, thank you very much for your talk and your paper.
Yeah, thanks for your question.
Okay, always a pleasure to have you here, Dr. Li.
Yeah,
Thank you very much for your talk. I think there are more questions.
Yeah, just one.
Okay,
so I very great talk. I learned from your talk that seems there are a lot of trade-off. I are trying to talk about how to complement and do trade-off between so many goals. But I feel in practice how we can merge this independent research to a single framework. And because it seems you publish paper in many different locations. You publish in private repository or public GitHub repository, and each intern or researcher write code in different ways. So how, as a researcher, how I can leverage your research result to further move forward? So this is one of my questions. Another question is that, do you have any suggestion for young researchers how to do research in this triangle? So you can see the triangle includes robustly, fairly. So what's your methodologies? So if I'm a junior researcher, I want to learn from you. So where should I start?
Okay, thanks, Troyan, for your great questions. So the first question, as you mentioned, maybe different interns, so they have different research projects, and they may write their code in different manners. Yeah, but in our team, I request them to develop code all in PyTorch, so we can, if there are designed also novel novel algorithms would be considered by the business units, so we can integrate their code and be optimized by the engineering team and deploy into our products directly. For the second question, as you can see, actually in the past 5 to 6 years, my main research areas are actually focused on these 3 topics in this triangle, mainly focusing on the privacy, robustness, and fairness. And indeed, I agree with your opinion that those 3 objectives, so they may conflict with each other, and it's very challenging and difficult to achieve multiple goals in one system together. But there is still a long way to go for the federated learning, right? Especially considering the different requirements from the business units. As a junior researcher, I suggest those students, so they can actually mainly focus on one perspective at the beginning, because each area is a very broad area. Privacy has a lot of attacks, defenses, and black box or the white box privacy attacks, right? Similarly for the robustness and the fairness, so from at the beginning of their research, so they can dig into one area. Later on, maybe at the third or maybe the fourth year of their study, so I always encourage those students so they can discuss with each other, they can learn from each other, so to make the whole system to interplay together. Because in reality, we still need to consider not only the privacy, but also need to ensure our build systems to be robust against the real world adversary examples. And also we want to win the trust from our customers. So we need to, and also for the collaborative fairness, we want to incentivize this participant to join in the collaboration. So we want to ensure fairness as well. I think all of them are quite important, but if from the research perspective, I always encourage the students to maybe focus on one area at the beginning.
Yeah, good suggestion. But in practice, I feel that I learned from some students that when they submit paper to some, for example, FL-AAAI, the reviewer may criticize that, oh, you only consider robustness, so how about the fairness, then get rejected. So these comments happen a lot in reviewing process. Yeah. So yeah, and maybe another angle is that in practice we don't need to consider all the aspects, because in some scenarios we need to emphasize, for example, fairness but ignore others. So depend on the requirement from the product side. So product side, yeah.
Oh, yes. I totally agree with you. So the research is research, and software development is software development. But always research go in the front before the software development. It's worthwhile to invest into the federated learning related research at the beginning, at least maybe 5 to 6 years before federated learning can be widely deployed in reality.
Yeah, thanks for your methodology suggestion. Thank you.
Thanks for your question as well.
Okay, thank you very much, Dr. Liu. Always a pleasure to have you here. I see there are a lot of interest in your work. And just one quick comment is that now we have a lot of attacks. We have a lot of defense mechanisms. Maybe it's a good time for us to conduct a cost-benefit analysis about how to deploy these verification approaches to defend against, to discover attacks, and to defend against the attacks. Because I have a feeling that the individual attack and defense works nowadays. There are a lot approaches available, but we need some kind of a coordination mechanism for a real-world federated learning system to be really able to defend simultaneously against these kind of attacks, which may or may not happen at any given point in time.
Yes, yes, I totally agree with you. That's a very good point. And always, not all the attacks actually they will work in reality. As I mentioned, there is always a gap between the research and the industry.
Okay, thank you very much for your invited talk.
Yeah,
I think
thanks.
Now I will pass on to Dr. Q-Sing from A-Star to continue hosting the remaining program. Dr. Q?
Yeah, thanks, Han. I think our next talk is about the communication efficient personalized federated learning, sparse training approach by Chen Tao. Let me introduce the Professor Tao first. Professor received his Bachelor of Engineering from University of Science and Technology of China, and his Master of Philosophy from Chinese University of Hong Kong, and his doctorate degree from University of London. Professor Tao currently is the director of the JD Explorer Academy and vice president of JD.com. He also advisor of the Digital Science Institute in the University of Sydney. He mainly applies statistics and mathematics to artificial intelligence and data science, and research is detailed in one monograph and have over 20 publications in the prestigious journal and proceeding and the leading conferences. Professor received the 2015 and 2020 Australian Eureka Prize, and also 2018 ICDM Research Contribution Award. He also is the IEEE Computer Society Main Klasky Technical Achievement Award. Professor Tao is a fellow of the Australian Academy of Science, AAAS, ACM, and IEE. Today, Professor Tao can't make it personally to this workshop. He have recorded video for us, so I will play the video. Can you see it?
Yes, we can see it.
Yeah.
Hello, everyone. Thanks for the conference committee's kind invitation. Today, I'm very happy to have the opportunity to introduce you something about personalized federated learning. Specifically, we will focus on communication efficiency. In this talk, I would first introduce the concept of personalized federated learning and its relation to general federated learning. Afterward, I will briefly discuss the basic idea of several state-of-the-art solutions for personalized FL and their downsides in the implementation of communication and computation efficient personalized FL. Then I would shed light on the high-level idea of our new personalized FL solution and how we fill the gap left by the current research. Finally, I will show the experimental results for the proposed solution. Let's get started with the general federated learning. The goal of general FL is to enable clients with heterogeneous local data distribution to collaboratively train one single global model. This global model is supposed to be versatile in doing inference on every local data distribution. However, the global model obtained by the general federated learning solution usually demonstrates unsatisfactory inference performance. This motivates us to raise the question, do we really need a global model that is versatile in every data distribution? Motivated by the gap left by federated learning, personalized FL has been proposed. The goal of personalized FL is transformed to collaboratively train personalized models for each client. The personalized models for each client are supposed to make accurate inferences on the client's local data distribution, but it has no responsibility to make efficient inference results over the overall data. For example, in the left figure, the red model is especially good at making inference on data with label 4. This red model demonstrates satisfactory performance when making inferences on the client A's local data, which is mostly labeled as 4. Another blue model in the right figure is good at making inference on data label as 6, which also demonstrates satisfactory performance on client B's data. Driven by the new goal specified by personalized FL, 2 research problems need to be addressed. First, how to design the personalized models for each client. Second, how to train the personalized models via the collaboration of a group of clients. The high-level ideas of personalized FL can be summarized into 2 core steps. The first step is how to extract public knowledge from the client's local data. The second step is how to inject the derived knowledge into personalized models. From existing literature, we summarize 3 kinds of personalized FL study, which we will explain with examples later. The first is layer-wise partition, whose basic idea is to separate a model into personalized layers and global layers. The second one is the regularization-based personalized FL, whose idea is to make the weights of a personalized model proximate to that of the global model. The third one is via model interpolation. The idea is, in essence, to make the model weights to be linear interpolated between global and local components. So the first one, personalized FL via layer-wise partition. Its basic idea is to partition model layers into personalized layers and shared layers. One typical example is that we can make the classifier of a model to be personalized and the feature extractor to be shared. Specifically, the model extractor is trained with a general federated learning solution, for example, Fed average. Well, the classifier is fine-tuned by each individual client, but its parameters would not be aggregated between clients. This training solution would enable the classifier to achieve better classification performance for the local data. However, for this kind of model partition solution, it's hard to derive the optimal partition of layers. The optimal partition could vary between models and datasets, which may compromise the robustness and generalization of the solution. The second personalized FL solution is called regularization. Its basic idea is to impose a regularized term into the loss function to make the weights of different personalized models proximal. By this means, each personalized model could share some common knowledge with the other, however, can maintain some degrees of the personalization. However, this regularization-based solution has its downsides. Specifically, due to the introduction of an extra regularized term, the local computation overhead would be increased. And in the training process, the clients typically maintain both local and personalized versions of models within the memory, so the clients may need to pay for extra memory if using this kind of solution. The third personalized FL solution is called a personalized FL via model interpolation. Model interpolation methods linearly interpolate weights between local models and a global model, where the global model can be viewed as the versatile global solution trained by Fed average, and the local model can be viewed as the models that minimize the loss over local training data. The general idea behind this solution is as follows. Given the fact that the global model may not perform well under the local data distribution, well, the pure local model may overfit the local training data, which also results in performance degradation. By interpolation, the obtained personalized models are enabled to adapt to the local data distribution via absorbing personalized knowledge, while simultaneously reducing the risk of overfitting the local training data via reserving the public knowledge. However, downsides still exist for this kind of solution. The clients are asked to maintain two versions of the model, and both of them need to be involved in the local training process. However, extra memory and computation are also required in this kind of personalized FL to achieve some reasonable performance. So, can we find an alternative solution to achieve personalized FL with no extra or even smaller computation, communication, and memory cost? Second, this particular issue drives us to propose FedSpa, a lightweight personalized federated learning solution. In our design of personalized models, we allow each client to maintain its personalized binary masks, which are specifically tailored to each client's local data. These masks are then applied or multiplied to a shared global model to produce the sparse personalized models for each client. In this way, the produced personalized models can reserve some degrees of global knowledge from the global model, while achieving personalization with the knowledge obtained from the personalized masks. Also, since some weights coordinate of the personalized models are masked with 0, the inference speed and this model could be accelerated. In the following, I'd like to detail the main procedure to train such sparse personalized models. The training procedure in one iteration is as follows. First, the server applies individual masks to the global model to produce the personalized sparse models for each client. Secondly, clients perform multiple steps of stochastic gradient descent to the personalized sparse models. Thirdly, clients apply mask searching technique to search for the new personalized masks. Firstly, clients send their next masks and the gradient update to the server. And finally, gradient updates are aggregated and applied to the global model. Here, I would like first to show how the server masks and distributes personalized models for the clients to do training. The above equation precisely depicts how the server masks and distributes the personalized sparse model. The model distributes to the clients personalized according to their masks. The benefit is that the models distributed to clients are sparse, and therefore the downlink bandwidth can be significantly saved. Then let's look into the procedure of local sparse training. The above equation precisely depicts the local update process. The clients would be asked to do multiple steps of SGD, like update to the sparse model. In order to maintain the sparse structure of the local models, we propose to multiply the personalized mask to the obtained stochastic gradient. In this way, the local models would be consistently sparse throughout the local training process. And we actually do not need to compute the complete stochastic gradient in real implementation. Therefore, the computation overhead in both the forward and backward process can be nicely reduced by our method. Next, I will detail how to do the mask searching. Here, we apply a method termed dynamic sparse training in the mask searching process. The following example would illustrate how it works to search for a good personalized mask. As indicated before, the client would do multiple steps of SGD to the sparse model, which are distributed from server in the beginning of a training iteration. Secondly, after local training is performed, we prune a certain number of parameters with the smallest magnitude in the model. These pruned parameters are deemed not important and can be safely pruned out for optimizing the local data distribution. Thirdly, we grow the number of new parameters that was pruned by the last stage in order to explore whether the already pruned weights are important for the local data distribution. So, finally, the next mask, along with the gradient update in this round, will be transmitted to server for later use. The mask searching process will be repeated with local updates. The above equation captures the aggregation procedure of the proposed solution. The gradient updates are averaged over the participants, and the average update is directly applied to the global model. Our solution can achieve smaller communication overhead, since the gradient updates from the participated clients are inherently sparse. To sum up, the proposed fed-sparse solution achieves personalized FL with reduced communication, reduced computation, minor extra memory, which is used for storage of binary mask, and even better accuracy performance. Next, I would show the experimental results of our solution to justify the above. claims. As shown in the figure, our feldspar solution achieves higher final accuracy performance in the non-IID setting over thousands of communication rounds. We simulated two groups of non-IID settings via gamma Dirichlet distribution named setting A and setting B. Setting A and setting B respectively specify gamma equals to 0.2, 0.1 for both EM list -L and CFR10, while specifying gamma equals to 0.5 and 0.3 for CFR10. We empirically find that feldspar with DST as the mask searching technique doesn't perform well in the IID setting. So we propose to plug in another mask searching technique called random stack mask, or RSM, to our feldspar framework. RSM is simply fixing the same mask for each specific client. So the method can be viewed as consistently training.
Sorry, everyone. There seems to be some network issue with the video playing. So I will try to play from my side from here onwards. So that hopefully the effect would be better. We go to the place where I think he left off.
As indicated before, the client would do multiple steps of SGD to the sparse model, which are distributed from the server in the beginning of a training iteration. Secondly, after local training is performed, we prune a certain number of parameters with the smallest magnitude in the model. These pruned parameters are deemed not important and can be safely pruned out for optimizing the local data distribution. Thirdly, we grew the number of new parameters that was pruned by the last stage in order to explore whether the already pruned weights are important for the local data distribution. So finally, the next mask, along with the gradient update in this round, will be transmitted to server for later use. The mask searching process will be repeated in the next time a client is selected for training. With multiple iterations of mask searching conducted throughout the federated learning process, a good personalized mask for each specific local distribution can be obtained. Subsequently, I will show how we do aggregation over the local updates. The above equation captures the aggregation procedure of the proposed solution. The gradient updates are averaged over the participants, and the average update is directly applied to the global model. Our solution can achieve smaller communication overhead, since the gradient updates from the participated clients are inherently sparse. To sum up, the proposed feldspar solution achieves personalized FL with reduced communication, reduced computation, minor extra memory, which is used for storage of binary mask and even better accuracy performance. Next, I would show the experimental results of our solution to justify the above claims. As shown in the figure, our feldspar solution achieves higher final accuracy performance in the non-IID setting over 1,000 communication rounds. We simulated two groups of non-IID settings via gamma dirichlet distribution named setting A and setting B. Setting A and setting B respectively specify gamma equals to 0.2, 0.1 for both EMNIST-L and CFR10, while specifying gamma equals to 0.5 and 0.3 for CFR10. We empirically find that feldspar with DST as the mask searching technique doesn't perform well in the IID setting. So we propose to plug in another mask searching technique called random stack mask, or RSM, to our feldspar framework. RSM is simply fixing the same mask for each specific client. So the method can be viewed as consistently training over the same subnetwork. Feldspar achieves similar results with a Fed average in all settings, but it still employs reduced communication, computation, and memory overhead like Feldspar. This table shows the communication rounds that different solutions each target accuracy for the first time. For example, this accuracy at 40 means the first time a solution reaches accuracy 40%. From the table, we see that our feldspar solution is useful in accelerating convergence rate in non-IID settings. Finally, the above table demonstrates how large and the communication and training envelopes for different solutions are throughout the training process. From the results, we can conclude that feldspar is useful in reducing communication and computation overhead. Now I can complete my speech. So thank you so much. I hope that a personalized FL can be valuable in many practical situations.
Okay, thank you everyone. Since Professor Torachan is not here in person, so we will not be able to have a Q&A session. So back to you, Singi.
Okay, I think next we shall go for another oral presentation session. I think the session chair is should be the Yang Chenyi.
Okay.
Okay.
Let's go to the second oral presentation session. And the first paper is towards general deep leakage in federated learning, and by Jiahui Geng, and the author have sent us a pre-recorded video.
I'm Jiahui Gan. I'm a PhD candidate in the University of Stavanger. So happy to have such a chance to share our latest research. Today, I come to talk about my late work last autumn in understanding the status of the practice leakage in the federated learning. And this is a part part of the memory correction to clarify. I include here some privacy enhancement technologies. Federated learning is a particular technology among these. Differential privacy is a data sharing method that can only share some statistical characteristics shared to describe the database without disclosing the information specific to the individual. To guarantee the differential privacy, it adds random noise to the original data for data release. Secure multi-party communication is a cryptographic protocol that distributes a computation across multiple parties, where no individual party can see the other party's data. Homomorphic encryption is a form of encryption with additional operation for computing over encrypted data without access to the secret key. The result of such a computation remains encrypted. Federated learning was first proposed by Google and was essentially a distributed machine learning paradigm. Federated learning updates the global model by sharing model parameters instead of the raw data through model aggregation. Federated learning has been used in many fields. The most typical case is the Gboard. When Gboard shows a suggested page query, you locally store the information about the concurrent text and whether you click the suggested. Federated learning processes the history of device to suggest the improvement to the next query. Federated learning is designed to solve the joint training problem of the silo region. Federated learning system consists of a computer server orchestrating the training process and multiple clients holding the private local data. Federated learning process repeats the following steps. First, the server selects a subset of clients and broadcasts the global model as the communication graph. Then the client executes the local training on its script data. Eventually, the server aggregates the models from the client and updates the global model. In this way, we achieve the privacy protection. Where there are many two approaches. One is called the FL-AAAI-22. The client computes the gradient and sends to the server. If we update the model multiple times before we send the model back to the server for aggregation, this method is called beta average. The first gradient sharing approach guarantees the convergence of the training, while the weight sharing cannot. Gradient sharing has higher communication cost since it has to communicate every iteration offline, while the model sharing reduces the communication cost. Deep leakage algorithm was the first implementation to prove that it is possible to obtain training data from shared gradients. First, dummy data and label are randomly generated after deriving the dummy gradients regarding to the dummy data and the dummy label. It updates the dummy data and label by matching the gradients. Eventually, the dummy data and labels will be very close to the training data and label. The algorithm is illustrated as in the left picture. There has been a series of studies on data construction text in federated learning scenarios. These attacks are white box attacks, with attacks on all model parameters and hyperparameters, including the learning rate and the model architecture. Any participant that has access to the shared model update can execute such attack. Deep leakage, the DLG was the first to recover both image and labels independent by gradient matching. However, their method is limited by the image scale and the batch size. The author of the IDLG found that the zero-shot label inference was more accurate when the batch size equals 1, but long-walk batch size greater than 1. The inverting gradient has demonstrated that it's possible to reconstruct images at higher resolution from the internet, from the ImageNet, no matter trained or untrained models. The total variation loss dramatically improves the quality of the large-scale match recovery. The latest work with inversion was feasible when the batch size was up to 48. It was also proposed a zero-shot label inference approach, but the approach requires that no matches in the batch share the same label, and the number of the classes must be greater than the batch size. By analyzing the previous work, we summarize the limitations as follows. Almost all the attacks are based on FL-AAAI and Federated. It's more widely used one. There are no work explaining what happens when duplicate labels create more batch, and no work explaining the mutual influence on label accuracy and the image restoration. This is our attack framework. In FitFTD case, the original brief data is XY, and the recovered brief data is X hat, Y hat. The parameters of the model is W, and the lambda W is the batch average gradient in the FitFTD scenario. The reconstruction function is consisting of gradient mesh loss and auxiliary regularization for the fidelity. In this paper, we propose a zero-shot batch label inference approach that is not constrained by the label distribution. We can infer the number of specific labels in one batch. The capital K is the batch size, and the capital N is the number of the classes. The smaller K and N are the corresponding index. The capital WFC delta, capital WFC are the weight and the gradient of the polyconnect layer. Capital O is the input of the polyconnect layer, and the O bar is calculated from the dummy data, as shown in the latest row. The left part implies the number of the samples where batch the label equals N in one batch, and we validate other values by feeding the dummy data into the network. We experimentally demonstrate that our approach works. The table 3 is a comparison between our method and the gradient inversion. Their methods does not spot the repeated labels in one batch, while our approach works. Table 4 demonstrated that our method works no matter the image scale with the number of classes is greater than the batch size. We experimented with the ImageNet and the Set10. Images from both data sets are copied to a given scale, and the optimizer for the local training is XGD, and the learning rate is 0.1. For image restoration, we choose the LBFTS optimizer, small efficiency in our work, and for the larger image, the learning rate is 0.1, and the attack update is 600. For smaller image, the learning rate is 0.5, and the number of updates is 300. More parents, you can see that from our paper. The figures demonstrated our results on ImageNet with size 16. The left and the right pictures are separated. The two rows above are the recovered pictures. The two rows below are the branch rows. There are no duplicate labels in one batch, and the recovered image is clean enough here with the branch rows. The attack in fit average is more challenging, more hyperparameters, more complex system. In the local multiple time update grows the gradient information. Assuming that the data held on a specific client remains consistent, we just use a simple strategy using the difference of two models to approximate the gradient and using sign similarity instead of the pair to distance. The results right side show that even after several local updates, the attack also works, and the attack became weaker after more local updates. In this work, we use 4 metrics to measure the similarity between the restored image and the original one. Since the reconstruction based on the matching or gradient matching cannot restore the sequence, and so the restored images are not aligned with the branch rows, we propose that the image, the pictures can be aligned based on the similarity of the picture. So we consider the alignment as a weighted by-party graph problem. The objective is to maximize the sum of the similarity in the back matching. In the right figure, the first 2 rows are the restored images, and the middle 2 rows are aligned with the branch rows in the last 2 rows. We designed 2 types of data distribution. Repetition represents the number of the actual repetitions, where the repetition equals to 0 with 3 images with the same label. With amount denotes number of occurrences of each label in batch. We found that the image with the same label are recovered as a fusion of images in our approach. The left figure shows the result of image recovery when with amount equals to for batch size 16. Here, the adjacent 2 images are of the same label. The right side table shows the result of image restoration when there are repeating labels in one batch. First value are for the gradient version. The second value is for ours. The duplicated label will make the restoration harder. That's all. Thank you for your attention.
Okay, let's go ahead to the Second paper by Sharman, Paul, and etc. Server-side local gradient aggregating and learning rate acceleration for scalable split learning. Please, Sharman.
Yes, I'll present my screen. Is the screen visible?
Yes, yes, please.
Okay.
Sorry, Shraman, the sound effect is not clear.
Okay, then I'll present it right now then.
Yeah.
Okay. So yeah, as moving forward, as I was saying, federated average includes multiple copies of a model present on multiple clients. These clients run their local iterations on their own local data set and send it to a central server for aggregation. The central server produces a global model which is sent back to the client for further iterations. So federated average performs pretty well with a large number of clients and achieves scalability, which in essence simply means that it improves the performance with the increase in the number of clients. However, when large models are considered, federated average is quite impractical because you would require large computational powerful devices for training these clients. On the other hand, split learning divides the model into multiple segments. For simplicity, let us assume that there are only two segments, out of which the lower model segment is present on multiple clients and the upper model segment is present on the server. So in sequential split learning, one client attaches to the server at one point of time and runs the iterations on its own local data. The lower model weight of the client is then sent to the next client in line, which utilizes these weights to train on its own local data set after connecting to the server. So sequential split learning performs well with large models because now we can break the model into smaller, lower segment to be stored on low resource edge devices which can act as clients, while the larger upper model can be stored on a single computationally powerful server. It also achieves scalability. However, as you can understand, the training time increases linearly with a large number of clients, which is quite impractical when a lot of number of clients are involved. To overcome this, parallel split learning involves connecting all the clients in parallel to the server. So this overcomes the large training time for sequential split learning. However, it fails to achieve scalability. One of the major reasons for this is the server client imbalance problem, which in essence simply means that the batch size of the server increases linearly with the number of clients. Therefore, the batch sizes can become very large at the server and fail to achieve scalability. To solve this, split federated learning, which incorporates aspects from federated learning and split learning, includes averaging the lower model weights that are present on the client. This solves the issue and improves the performance. However, as you can understand, it also increases the communication cost of the clients. And there is another added problem to this, that we term as the backward client decoupling problem, which in essence simply means that when the backward passes for the different clients are performed, they become detached at the server side or the cut layer of the server side, which is basically the first layer of the server. Therefore, there is no information flow between the different backward passes of the different clients. That is why to solve these two problems, we suggest two novel frameworks called split LR and split average, respectively. First, coming to split LR, it in essence simply means that we introduce different learning rate schemes for the server and for the
your slides are not moving. Can you also move your slides along the way? Yeah, it's still at this page number 2.
Okay, I have actually moved. Let me see.
Oh, because there could be some delay on, yeah.
This is moving right now?
Yeah.
Okay.
Next.
So yeah, in literature, the two most popular linear rate algorithms, two most popular learning rate scaling algorithms are the linear scaling rule and the square root scaling rule. So as we apply the learning rate acceleration for only one part of the model that is present on the server side and not on the client side, we assume a general equation and we find the optimal value of alpha experimentally. Later on, we'll show that the value of 0.5 and 1 perform the best, which is in correspondence with the current literature. The next and the more important algorithm is the split average algorithm. It simply takes a subset of the clients or all of the clients and aggregates its gradient into one global gradient. So instead of getting the local gradient, these clients now receive the global gradient. So the global gradient infuses information from the gradients of multiple clients into one. Therefore, there is flow of information during the backward pass from one client to another. Therefore, this solves the backward client decoupling problem. This also helps additively to reduce the communication overhead from the server to the client. As we break down let's say for example, 5 different local clients into one global client, which is of the same size as the local gradient of the clients. So I'd like to present some experimental results that we obtained in our paper. This is based on the Fashion MNIST paper and the CIFAR 10 paper. So the first plot on the top left is on the CIFAR 10 dataset. So we have compared the performance of the different methods across a varying number of clients. So as we can see, sequential split learning achieves scalability. However, the performance is quite poor. And as I said earlier, the training time is quite large. On the other hand, split federated learning improves the performance, but it is not scalable. So as you can see, the performance decreases when the number of clients exceeds 40. On the other hand, in our method, the blue one, the performance keeps increasing with the number of clients. On the plot on the top right, we have shown how the performance varies by increasing the number of parameters or changing the number of parameters for a split average algorithm. So phi essentially means the fraction of clients that participate into the aggregation of the global clients, but for the global gradient. So as we can see, a fraction of 0.75 and 0.5 performs the best, which in a sense means that taking 75% of the clients to form the global gradient improves the performance the most. On the table, we have shown a small score performance comparison on the Fashion MNIST dataset. So for 20 number of clients, the baseline score was 84.88%. After including split average, the score improved by 1.71%, and adding split LR on top of it increased the score by 0.898 by more. So as we can see, the two algorithms can additively increase the performance from the baseline. So this is a small comparison of the communication efficiency of the different methods. Our method is more efficient than all the other split learning frameworks that are shown here. However, when compared to federated learning, it depends on the model size, the dataset size, and the number of clients that are involved. On the right-hand side of the plot, we have shown how the efficiency or the communication overhead increases or decreases based on the different parameters. When all the clients are utilized in the split average, the efficiency is the highest. However, there is a trade-off with the performance. This is a comparison of the training time of the different methods that we have discussed so far. We vary the dataset sizes from 25,000 to 2 million. We also vary the number of clients and keep it 20 or 100. And we also vary the model sizes from 100 to 200. So as you can see, when the number of samples are quite less, that is 25,000, 50,000, our model takes a much less amount of time compared to federated learning or other split learning frameworks. However, when the number of data samples increase, federated learning can become more efficient, but however, that can be offset by our algorithm by increasing the number of clients. On the right hand side, we've also shown a plot for the computational cost per client. So as we can see, federated learning has the highest among all the other decentralized methods, while in general, split learning frameworks have the least amount of computational cost per client. So this is in tandem with using low resource devices as clients can be pretty practical when split learning frameworks are considered. So finally, we have a comparison for the information leakage. where we use an autoencoder for reconstructing the input from the output of the different clients. So as we can see, by increasing the fraction of split average, that is by incorporating more and more clients into the global gradient formation, we increase the loss for the autoencoder, which in essence can be a proxy for saying that it becomes tougher for the autoencoder to form the input image from the output of the client. So we can say that it decreases the information leakage by increasing the number of clients that participate in the global aggregate formation, global gradient formation. So in conclusion, we have proposed a novel framework which involves two different algorithms, split LR and split average, which addresses the server side large batch size problem, which is the server client imbalance problem, and the backward client decoupling problem respectively. We've also shown that there is less information leakage when we involve a larger number of clients with using the split average algorithm. We've also shown that there's a higher communication efficiency than the other SL frameworks and also federated learning in some cases. In future work, we plan to include different split LR methods, which can include cyclical learning rate. We also plan to include differential privacy analysis on the split average and see how it can affect the privacy analysis for the different parameters of the settings. So finally, I would like to thank all the authors present here, without whom we would not have been able to build our paper on. Thank you.
Thank you. Any questions? Okay, thanks. Thanks again. Let's go ahead. The third paper is tackling Mavericks in federated learning via adaptive client selection strategy by Jiyue Huang, Chi Hong, Yang Liu, and Linda Y. Chen, and Stephen Roos. Please.
Thank you. Can you see my screen?
Okay, please go ahead.
Thank you very much. My name is Zhiyue from TU Delft, and I'm glad to share our work, tackling Mavericks in federated learning via adaptive client selection strategy. Let's start with what is Mavericks? Here comes a paper as a practical case. It addresses that rare disease research is threatened by proposed changes to European privacy laws. And some other related reports has also shown that data, especially real data, is as limitation for research and application. To cope with this, some organizations such as NORD has been authorized to create a rare disease database for some research use exclusively. According to this phenomenon, we know that not all classes of data are rare, and some common data are available everywhere, such as in the medical field. Headache data and stomachache data are common, and the real data are usually owned by specific organizations exclusively. And how can this setting link to the popular research? The popular data distribution settings in FL research is IID, unbalanced in quantity, and non-IID in data labels. And we ask, do they cover the mentioned real-world distribution, such as the rare diseases? The answer is no. So this picture illustrates our concepts of Maverick. For the blue part, which is the non-Maverick, it has the common data distributed, and the green part is the Maverick, which besides the common data, it has massive exclusive class data, and it can also be extended as the shared Mavericks, which means the exclusive class was shared among a small group. According to this, it has three properties: exclusive class, larger quantity, and more skewed distribution than the non-Mavericks. We can also generalize the Maverick setting. That is, if everyone is shared Maverick, then it is IID setting. And if everyone is exclusive Maverick, then it is the typical one-class non-ID distribution. But in this paper, we only focus on the general Maverick case and ignore the extreme case. So how can we improve the learning with Mavericks in an FL system? The most straightforward solution is adaptively involving clients of different distribution by adaptive client selection. Client selection in FL can be categorized as contribution-based or distance-based. For the contribution-based, the most popular is for influence and shapely value. In this paper, we focus on the analysis of the shapely value measurement because it was the sequential averaged version of the influence measurement. And it has also been verified to be more effective in the state-of-the-art measurement of contribution in FL. And this is the definition of shapely value. According to the definition as well as the concept of Mavericks, we got a property that we analyze the property that shapely value and influence share the same trend in the contribution measurement of Mavericks. Combining this property and the previous three properties, we derive theorem 1. That is, the shapely value measured by for the Mavericks is less than the non-Maverick in the beginning of the learning phase, and it gradually converges towards to a non-Maverick. And our experimental results has also verified this finding. But we found this is not reasonable because the Maverick has the exclusive class, which is important to the task, for example, the classification task. Then we proposed the novel FED-EMD algorithm. It is a distance-based way where the distance measured here is by the Wasserstein distance according to its benefits. It has three factors. The first is the constant global distance, and the second is the dynamic current distance. We also involve a round decay to avoid non-convergence. It has three steps: distribution reporting and initialization, dynamic weights calculation, and the weighted client selection. For more details, please refer to our paper. And for the FED-EMD algorithm, we also derive theorem 2 as the convergence guarantee of the FED-EMD. Then let's go to the experimental evaluation part. Table 1 is the convergence round of the selection strategy. FED-EMD achieves the least rounds for reaching the highest accuracy, while the new baseline FED-FAST sometimes even do not reach the 99% of the highest accuracy. The reason is analyzed, and this is from the KDD 2020, it's very new. And the second result is the comparison of the FED-EMD and the shapely value-based way. We found that the FED-EMD outperforms SVB in different aggregations. This is within our expectation of the theoretical analysis. And the FED-EMD is also effective over sensitive hyperparameters. In the picture is the beta. It is designed in our algorithm. Also, there is a result to demonstrate the effectiveness on multiple Mavericks. FED-EMD need fewer rounds to converge on both multiple shared and multiple exclusive Mavericks. And since our results are done in 3 replications, we have also recorded the standard deviation among different results. FED-EMD have smaller standard deviation than other baseline method, which implies a better stability. This is the summary and the takeout ideas of our paper. And if you are interested in our paper, you can refer to the to the paper. Thank you very much for your attention, and I'm glad to have some questions.
Thanks, Ji Yuan. Any questions? Okay, then we'll move to the next paper. FedCG leverage conditional GN for protecting privacy and maintaining competitive performance in federated learning by Yue Zhou Wu, Yan Kang, Jia Huan Duo, Yuan Qin He, and Qiang Yang. Please share your screen. We cannot hear you, please.
Can you hear me right now?
Okay, please. Okay.
Okay, can you hear me? Okay, can you see my screen?
Okay.
You can see my screen right now?
Yeah.
Okay. Let's see. Okay. So my talk today is about the FedCG leverage conditional GAN for protecting privacy and preserving performance in federated learning. So the main problem we want to solve is that in the horizontal federated learning scenario, we want to protect the privacy while at the same time preserving the performance, the model performance of each client. In the conventional federating algorithms such as Fed-average, Fed-prox, they typically share the whole model with the server. This might leak data privacy of each client, and also the federated learning privacy preserving methods such as DP and Fed speed. They can, although they may protect the privacy to some level, but they may lead to degradation of the model performance. So we propose a method called FedCG. The core idea of FedCG is that it decomposes each client's local model, local network into a private extractor and a public classifier. This is similar to Fed3 speed. And the novel part is that each client leverages a conditional GAN to approximate the generator to the extractor, and each client share its generator with the server rather than sharing the extractor. So the purpose is twofold. One is protect privacy because share client generators with the server provides a high-level privacy preserving capability. We will show the experimental results later. And another purpose is to preserve the performance. So on the server side, the shared knowledge, the server fuse the shared knowledge by aggregating client generators and classifiers, which in terms would help clients improve the performance of their local networks. So the training procedure involves two major steps. One is two-stage client update. Another is server aggregation. So on the two-stage client update, it involves the first stage is update classification network. We have two losses to minimize. One is the main classification task loss. By minimizing this loss, we optimize the classification network, which include the extractor and the classifier. And by minimizing another loss called MSC loss, we want to put together the output distribution of the extractor and the generator. This aims to integrate the shared knowledge encoded in the global generator into the local extractor to improve the performance of the local classification network as a whole. The second stage is to update the generative network. So this is just we follow the normal training process for conditional GAN. Except that we approximate the output representations of the generator to those of the extractor. This aims to share the generator with the server to protect client data privacy. So we will not send out the extractor to the server, because the extractor is trained directly by the origin data. It will leak the data privacy. So on the second stage, the server aggregates the client's generators and classifiers using knowledge distribution. So the server aggregates shared knowledge to help in the next round to help clients to improve their network performance. It's noted that so on this stage we do not need any original data, but we need to enable, because we need to train the conditional GAN. We need to fuse the conditional GAN of all the clients. So for the experimental setting, for now we use NANET as the classification network. The first two we treat the first two convolutional layers as a private extractor, and the next three fully connected layers as a public classifier. For the generative network, we use conditional DC GAN. We use five data sets for our experiments. The cipher and the F-minst is for the IID setting, and the digital file and Office 10, the domain net, are for the non-IID settings. The digital file of Office 10 and domain net data sets, they are formed by data from different domains. Therefore, they naturally form the non-IID settings. For the FL baseline, we adopt two lines of FL methods. One line includes the FL methods that share the whole network, the whole model with the server. These methods include Fed-average, Fed-prox, and Fed-df. And another line of work include the FL methods that share only partial model. So the top partial model with the server. So these work include Fed-speed and Fed-gen. Our Fed-CG belongs to this category. But in addition to the partial network, we also share the generator with the server. So we will test if sharing generator with a classifier, we can still preserve the privacy. So for the experiment results, so overall, Fed-CG achieves the best accuracy in 4 out of 6 settings, half for the IID settings, half for the non-IID settings. So from the table on the bottom, we can see that the Fed-CG achieved the best accuracy on the Fed-minst data set. Although its Fed-CG is not the best, it's not the best performer on the cipher-10 data set, but it's not far away from the best performer, which is the Fed-prox. For the non-IID settings, Fed-CG achieves the best accuracy in all 3 non-IID settings. Particularly, it outperforms the Fed-CG outperforms the second to best performing algorithm, Fed-prox, by 4% on the Office data set. So let's dig deeper into how Fed-CG performs on each client. So the figure shows that. So the figure shows that the 5 figures show that shows the accuracy gains achieved by various federated baseline and our Fed-CG over local model of each client. The positive gain means that the FL method achieve better performance than the local model does. So the negative gain means that the FL method achieve worse performance than the local model does. So for IID setting, the first row, the two figures on the show that all FL methods outperform the local models across all clients by large margins. The FCG performs the best on all clients on the F means the data set. So which shows in this figure, the figure A. And the performance of FCG is not the best on the Cypher-10 data sets, but is not far away from those of FL methods that share the whole model with the server. So like the Fed average, Fed proxy, and Fed DF. So for the non-IID setting, no FL methods that can be the local model on all clients across all three non-IID data sets. But FedCG achieves the best results in terms of the number of local model it outperforms. So for evaluating the privacy, we adopt PSNR as the metric to measure the privacy leakage. So lower the PSNR value indicates less privacy leakage. So we measure privacy preserving capability of each method or each FL method against the DLG attack. DLG stands for the deep leakage from gradients. So we compare our FedCG with Fed average and the Fed split. The Fed average here represents a family of federated learning algorithms that share the whole model with the server. While the Fed split it represents a family of FL methods that share the top partial model with the server. So from the figure on the right, we can see that the Fed average cannot. They cannot protect the privacy. It's pretty easy to recover the original data by using DLG attack. Although we can add DP noise to protect the privacy, and while we add more DP noise, the privacy can be better protected for Fed average. But this results in a serious loss of accuracy, as we can see on the bottom table here. For Fed split, we cannot. The DLG attack cannot recover the original data, but it comes with a non-negligible loss of accuracy. While on the other hand, the FedCG can protect the privacy while achieving a competitive model of performance, as shown on the bottom table. So for the future works, currently we only utilize NetNet as a local network. So in the future, we will investigate deeper neural networks to further examine the effectiveness of the FedCG method. And also, we here in this work, we empirically prove that the FedCG can protect privacy against DLG attacks. But in the future, we will provide theoretical analysis on the privacy guarantee of FedCG. Okay, that's all. Thanks.
Thank you. Any questions? Okay, let's go forward to the fifth talk. Words of Better Help, context-aware client selection for federated learning by Han Ruicao, Qi Yingpeng, Yifei Zhu, and Jiang Chuanliu. Please.
Okay, thank you. So hi everyone, I'm Han Ruicao from Shanghai Jiaotong University. We are honored to be here to introduce our work on federated learning, Words of Better Help, neural combinatorial contextual bandit selection for federated learning. This work is supervised by Professor Yifei Zhu, and it is also joint work with Professor Jiang Chuanliu from Simon Fraser University. The first federated learning emerges an effective tool to train neural networks among edge devices without centralization of the data. In federated learning, the devices basically they will send the weight update to the global server. Instead, no raw data will be shared in this process. However, what we are going to solve is the challenge of the non-ID data, which refers to the non-independent identical distribution of the data. Particularly, we'll focus on the, this is also known as a data heterogeneity issue with the non-data has severe consequences on various aspects of federated learning, including the suboptimal prediction performance, the longer convergence time, and the unfairness issues. So there are recent works on federated learning. They improve some of the works have some limitations. For example, some of the proposed work, like the local weight update work, still assumes that data follows the IID distribution. Then other methods leverage the posterior information, like the model weights, or use the cluster FL and to improve the selection. But some of them cause the overheads and are not efficient. So what we are going to do is we try to figure out an efficient approach to resolve the issue with non-ID data in federated learning setting. So to resolve the problem, we first draw the motivation that different local client datasets might have some correlation. For an intuitive example, we can see if we are evaluating two NLP datasets, like there are two datasets, one is from the two journalists, another dataset is one from journalist, another one from one professor. It is very intuitive that the latter one will yield a larger corpus difference. If we are going to train a globalized NLP model in the federated learning setting, it's probably better we'll select the one with the larger corpus. And this also works for the image dataset, where the image captured by the same scenario, will also share some similarity. So actually, this issue is examined in the linguistic analysis. Well, in the social network, when two friends they are saying something, what do they say? The dataset might have some correlation, which may affect the machine learning training performance. So we observe this and we say, if we could capture this type of correlation and consider such correlation with selecting the clients, maybe we can get a good global model can be trained, and we can represent more clients with fewer communication rounds by the smart selection. However, this intuition has some challenges. One is, how can we capture the correlation among local data sets privately? We know that in the federated learning setting, we cannot directly use the client's data set. It has a very strict requirements on the privacy issue. And also I wonder how to leverage in the correlation to help the federated learning. This is actually a non-trivial relationship learning. We know, although there are correlation between data sets, it does not have a very trivial relation with the training performance. It's not it's not like it's a very linear relation. It's a non-retrieval one. And also, this is a combinatorial constraint that we need to select M clients among N clients, which makes the client selection much harder problem to solve. To resolve this problem, we propose a neural contextual combinatorial bandit approach, which can encode the information of previous client's data and also improve the client selection strategy. Basically, there are two sub-modules. One is the contextual feature extraction with privacy processing module, and another is the client selection module. Basically, our model works in the four steps. Before the federated learning actually starts, each local device will upload their privacy encoded features to the global server, which will serve as a contextual features into the bandit. In the step one, the global server will broadcast the model to each client device, and for each devices, it will calculate the contextual features, and feature actor will be input along the local model. It will be input to the along with the local model update to the neural reward estimator. In step three, the local device will not only upload their data weight update, they will also upload the loss, the train in the local data set to the neural reward estimator for the calculation of the actual reward. The neural reward estimator will learn to associate the features with the calculated reward. And the client selector will make their decision of the selection clients participating in the next round. In short, we actually form this problem, view this client selection problem as a multi-arm bandit problem. And the context will be it is not just a simple bandit problem, but it will be a contextual bandit, where the context will be the privacy preserving features of the data sets of the clients. So if this is the case that if the client changes the data set, the contextual features will also need to be updated. So let's look further into the module of this architecture. So first is how can we privately extract the data features. We use a strategy called the local sensitivity hashing. It is a very lightweight approach to hash the text into the n-dimensional features. To better illustrate this, I'll provide a very toy example. Is that here's a sentence like the test set on the map will calculate the corresponding hash values and use the LS hash. It will be mapped to an n-bit hash number, and this number can be input as a n-dimensional vector to the contextual bandit. And this is verified linguistically that if the two text data set has shared some linguistic similarity, their hashed value will also have some correlation. Like there will be this hashed value can be used to represent the features without actually reviewing the information of the data sets. So in this way, we can provide the textual data features to the server privately. And let's go to the second part is the neural combinatorial contextual bandit. So this is actually a pipeline of two parts. One is the neural reward estimator, another is the client selector. So if previously in the initial round, we will randomly select clients, and the select clients they will calculate the contextual features privately, and they will also do trainings locally with some training loss. And after they finish the training, they'll upload their training loss contextual features along with the training weight to the neural reward estimator. The neural reward estimator job is to fit the relation between the contextual vector versus reward. Actually, the reward, you may ask what is the reward in our context. The reward is how we define the utility of each client. If the client has a larger reward, it is a function associated with the loss. And for the details of the reward, you may refer to the actual paper. And if the client has a larger reward, it is believed to perform better in the training in the federated learning setting. And for the neural reward estimator, its job is to fit the contextual vector versus the reward. And after they finish the fitting, they will upload this. The client selector will use the neural reward estimator to select the clients based on the prediction of the sum of the rewards. Like the neural reward estimator will give the even it can predict the rewards for the unselected clients based on their privately encoded data features. So the job for the client selector is to maximize this reward. And actually in this, to ensure the fairness issue, we also set a counter for each cluster clients to ensure that one cluster clients will not be selected for 2 million times. And for the details of implementation, you can refer to the actual paper for the details. And for the evaluation of this, we performed our evaluation on the NLP task for the next word prediction on the super user and the op data set. We simulated the federated system that each user will represent the client in the federated system, and their textual data, including comments, posts, and local client data. And they will be, we use the stacked LSTM model for each client user for simulation. And for the experiment, we compared with other bandit approach like the AUT, which is another bandit approach for federated learning, and the federation average benchmark. And also we'll plan to implement more benchmarks in the future. And we evaluated the performance based on top K accuracy and round-trip audit speed, and also performed some sensitivity analysis on the controllable parameters like the input that the size of the total participants and the feature size. So this is this is some partial results of the methods. It's showing that our methods has reached the high accuracy on the task of the network prediction, and also it works well for the different scales of the participant setting. And to sum up, we propose a novel combinatorial contextual bandit approach, which is an computation-efficient federated learning approach by using the correlation from the clients privately. Our method works well, handles the non-trivial relationship between the privately encoded features and the reward, and works well in the intrinsic combinatorial sequence space. Our method ensures the privacy environment increases the accuracy, conversion speed, meanwhile it is also a very lightweight approach without much overhead. So this is a reference for this presentation, and thank you for listening.
Thank you for your talk. Any questions? Okay, let's move. The sixth talk, improving fairness via federated learning by Yu Chen, Zheng, Hong Xu Chen, and Kang Wook Lee. Please share your screen.
Okay, hello everyone. I'm Yu-Chen Zheng from University of Wisconsin-Madison, and I'm here to present my recent work, Improving Fairness via Federated Learning. And this is a joint work with Hongxu Chen and Kang Wook Lee, my PhD advisor. And if you are interested, you can scan the QR code of our full paper, which is available on arXiv. Okay, so first let me just, give you a quick overview of quick guidance of what is fairness. So AI algorithms have a long history of being unfair regarding gender, race, and ethnicity. And this is a quick example. The white man on the left has committed 3 serious felonies, and the black woman on the right has committed 4 juvenile misdemeanors. However, the AI trained risk assessment instrument tool predict the white man to have very low risk of reoffending, but predict the black women to have very high risk of reoffending. And actually, there was one survey made by ProPublica shows that the forced jail decision rate for the black women is twice as the forced jail decision rate for the white people, which is unfair. So to address this issue, actually, there has been a large amount of work in training fair classifiers. And I'm gonna introduce one most commonly used fairness notion, which is called demographic parity. And let's use A to denote the sensitive attribute, which could be the gender, race, etc. And use Y to denote the label, which could be the release or incarcerate in the context of recidivism. So the demographic parity basically requires the equality in the positive rate among different groups. And in the context of recidivism, you can imagine that the demographic parity basically requires the incarcerate or release rate to be equal among different race groups. So if we measure the unfairness using the absolute difference between the positive rate, and actually most of the fairness-aware algorithms aim to mitigate the bias of this classifier from one centralized training data set. But the question is, what if we cannot get access to the entire training data? Because now we don't know the positive rate of different groups. So how to train a fair classifier from decentralized data? That's one question. So actually, I will give you a quick example why we cannot get access to the entire training data set. So for example, there are 3 local banks, and each of them may own some local private user data, and they are not allowed to share those private data with each other. So how to learn fair classifiers from decentralized data? Even before we move on to federated learning, one natural question arises: is federated learning even necessary at all to learn a fair classifier? So first, we
propose one baseline method without incorporating federated learning, which is local fair training plus ensemble, and we call it LFT plus ensemble for short. So basically, we just perform fair training on local data set and get some locally fair classifiers, and then we ensemble them to get a global classifier. So in contrast, we also employ Fed average to show the necessity of federated learning. So this method is called LFT fair training plus Fed average, and we call it LFT plus Fed average for short. So basically at each communication round, so for local update, those local clients will perform fair training, and at each communication round, the server will take the average of those locally fair model parameters. And this kind of information exchange happens periodically. And besides, we also provide one more baseline method, centralized fair learning, so which basically put all the data together and then perform fair training on the centralized data. So of course, this method will serve as the upper bound of the accuracy fairness trade-off, because this method enjoys more flexibility. So for now, it is clear that in terms of privacy, we can order these three methods this way, because like LFT plus ensemble is the most private because it only requires information exchange once to ensemble the locally fair model parameters. And the centralized fair learning, CFL, is not private at all because those data owner just exchange the data directly. And the LFT plus Fed average will be something in between. But how about fairness performance? To answer the question we just proposed, whether federated learning is necessary at all, we perform some theoretical and numerical analysis of these three methods. So we assume two clients with different distributions, and we use this figure to summarize all our findings. So the x-axis is the global unfairness, and the y-axis is the accuracy. If you look at the orange curve, which represents the LFT plus ensemble, you may notice that for the leftmost figure, it fails to reduce the unfairness to a very low level. Say it is strictly greater than 0 compared with the other two methods, right? And besides, it also only achieved the lowest or worst accuracy fairness trade-off. And another phenomenon we observe is that as the data heterogeneity goes up, we find the performance of LFT plus Fed average also become worse and worse. And there is also a significant gap between the CFL and LFT plus Fed average when the data heterogeneity become very high. So to summarize, so in terms of fairness, we find we can order these three baseline methods in a reverse order. So the CFL can have the best fairness performance, and the LFT plus ensemble has the worst fairness performance. And the first strict inequality actually shows that federated learning is necessary for achieving fairness. So this is kind of stark difference from the previous finding about federated learning, because previous federated learning basically just make use of the large amount of data sets from many clients. But now we only assume two clients. The federated learning is still able to make full use of the data diversity to boost the model fairness. And another conclusion we can make is that the LFT plus Fed average is not sufficient because there is a significant gap between this method and the CFL. So our another main contribution is that we propose Fed FB, which breaks the limit of LFT plus Fed average and achieves similar performance as CFL while ensuring the privacy. So our FedFB is based on a centralized fair learning method called FedFB, or fair batch, which reweights the samples by solving a bi-level optimization problem to mitigate bias. But I won't go to the details of the mathematical formulation. But instead, I will just give you a quick idea of how reweighting mechanism works. So suppose that we know that the positive rate of one group is higher than another. What we can do is we can increase the weights attached to the positive samples from the disadvantaged group. And this will result in the rise of the positive rate of this disadvantaged group. And we can also reduce the weights attached to the positive samples from the advantaged group. And in this case, we can reduce the difference between the two positive rates. And in this case, we can reduce the bias. But the main problem is if we cannot get access to the entire training data set, we have no way to evaluate like which group enjoys higher positive rate. So to evaluate this condition, the basic idea of our approach is we can let each data owner to share the loss of each group during the training. And then we can make use of this additional information to estimate the relationship between the positive rate. So in addition to model parameters, FL-AAAI extend the group-specific losses as well. And to evaluate the performance of our approach, so we just plot the accuracy fairness trade-off of our method together with CFL. And we find that our FL-AAAI nearly matches the performance of CFL. And we even developed a more private version of our FL-AAAI, which only exchange 10 bits of information at each communication round. And we find this even more private variant of FL-AAAI can also achieve kind of good performance, like achieve similar performance as CFL. And this is the summary of our work. So we can see our FL-AAAI like enjoys good privacy but achieve much better accuracy fairness performance, which like very close to the CFL. So that's the end of today's presentation. And I'm happy to take any questions.
Thank you. And any questions? Okay, this is the end of the second oral presentation session.
Okay. Thanks, Jenny, to host this session. So our next is the invited talk, by Nicholas Cardini. The talk is about challenges in privacy with distributed training data. Let me briefly introduce the Dr. Cardini. Okay. So Dr. Cardini is now a research scientist at Google Brain. He studied the security and privacy of machine learning. He have received best paper award at ICML, Usenet Security, and IEEE S&P. I think some of his work also been featured in the New York Times, BBC, Nature magazine, and Popular Science, and many more. I think he obtained his PhD from UC Berkeley in 2018. Also, he received his bachelor in computer science mathematics from UC Berkeley in 2013. Without further ado, Nicholas, are you there?
Yes, I'm here.
Yeah, stay at your, yeah.
Thank you. Let me present my slides. Okay, you can see?
Yes.
Great.
See.
Yeah, okay, happy to be here. So I'm going to talk about some challenges in privately distributing training data. So the basic premise of this talk is very much in line with what the workshop is focusing on, where we have two parties, A and B, and we'd like them to somehow be able to each have their own training data sets and allow them to collaborate in some way so that through their collaboration, they can jointly train some machine learning model that's better than the model that each of them could have trained individually, but without actually revealing
their training data sets to the other party. Right, this is the general framework of this distributed machine learning that we're all trying to solve. And now, one you could try and do this is what most people try and do now, which is some combination of federated learning and differential privacy and multi-party computation. And this basically works. A bunch of people have been working really hard at improving this, and we more or less understand how to do it. The problem, though, is it ends up being somewhat complicated because you have these two parties and they each have their training data sets, and they have to exchange a bunch of messages back and forth in order to even get federated learning to work. And like if you're going to do like MPC, like you sort of just have messages on top of messages, sort of everything's going crazy in order to have privacy. And there's a bunch of really good work trying to make this easier, but it's still rather challenging. And so there's another research direction that tries to ask if we can achieve the same results without having to rely on some of this really sophisticated techniques. And what this technique does is it tries to just directly distribute the training data to the other parties. Now, obviously, sending the other person my training data is not going to work. Like this is going to violate the privacy by training data. So instead, what we're going to do is we're going to try and send an encoded version of the training data set. Okay, so what do I mean by this? We each have our parties A and B again, but now what's going to happen is each of the parties are going to somehow encode their training data sets through an encoding function that's going to give some noisy data set that has the property that the encoded data set reveals nothing about the original data, but machine learning models can still be trained on it. This is kind of magic that you can do this, but let's suppose for the time being that you can. Then what you could do is you could directly take these encoded data sets, share them with each other, and just train machine learning models on these encoded data sets, and everything would be fine. The question, though, is how do you construct an encoding function that simultaneously preserves the privacy of the data, but is also allows machine learning models to train on these encoded data sets? And okay, so first of all, it's kind of weird that this gives a usable machine learning model in the first place. Like these images here look completely noisy. How is it that machine learning models are able to learn on these? And I agree, it is weird. I'm not going to focus on that in this talk. Let's just sort of accept on faith the authors have done their due diligence and have shown that you can actually learn correct, good information from these models. They're useful. The question is, are they private? Like, do they actually respect their privacy guarantees that they are claimed? And for this, I'm going to sort of walk through two case studies in this talk where people have tried to achieve these kinds of results and show why it is that these schemes have failed, and hopefully draw some lessons for what future schemes might be able to achieve in the future. Okay, so first case study is going to be a scheme that's called InstaHide. It was released about 1.5 years ago now, and it tries to do exactly this problem in the way that we've described. So we're going to take an image, we're going to encode the image, and then we're going to reveal the image to anyone who wants it. And they can then train their machine learning model on this encoded image. And again, the idea is that the reason we should expect this gives privacy is that even if you had access to the machine learning model, you should never be able to recover the image, because like the best you would be able to do is to recover the encodings, and these encodings are designed so that the encoding cannot reveal the original image. So as long as you train with this way, you don't need to do MPC, you don't need to do differential privacy, everything is fine, you don't even need the fancy federated learning stuff, you just encode your images, send them to anyone who wants them, and just sort of publicize this data set because it's been made private. Okay, so the question is, does it work? And for this, let me start by telling you how InstaHide works. What InstaHide is going to do is it's going to construct, it sort of starts off with its private data set. These are the images that are sensitive that I care about. For this talk, I'm going to show examples of CIFAR-10 images, just sort of for convenience. But you can imagine that this was sort of any private data set that I might actually have. So we take these private images, and we also then go for InstaHide, and we just crawl the internet and just find some public images. These are any images that we want that we can find online. Now what InstaHide does is it's going to take a couple of images from the private data set, a couple of images from the public data set, and compute a linear combination of these images in pixel space. So we sort of randomly add together these images and sort of smash them all sort of on top of each other. And this gives us a very noisy image that has sort of components of each of the images that are being added together. And then just to add a little bit more security here, InstaHide does this random pixel flipping operation and adds a little bit more noise to each of the pixels individually. And then it sort of takes this image as one encoded image and sticks it over to the side and says, okay, this is the first image of my encoded data set. And then it does the same thing again. It takes 2 new images from the private set, 2 new images from the public set, computes a linear combination of these, adds noise, and sort of takes this as another point that's going to be released in the encoded set. It then does this a number of times until you end up with a fairly large collection of images, which are your encoded images that you can release now to anyone else in the world. Now, in order to achieve utility, you have to attach some kind of labels to these. The labels are also a mixed combination of the labels of the private images, but again, I'm not going to focus too much on how to get something useful out of this. I'm going to focus on what the privacy of the algorithm is. Okay. So how do we go and attack this? And this is something that we wrote a paper on last year to analyze. And basically what we're going to do is we're going to show how to take one of these encoded images and actually directly recover almost completely perfectly the original image that constructed it. We're going to do exactly the inversion operation that InstaHide was designed to prevent. And the way we're going to do this is relatively straightforward. The first step in our attack is going to be to try and cluster together encoded images that shared an original image in common. So what do I mean by this? What I mean is, we're going to try and train a neural network F, some function F, that has the following property. If I pass in 2 images that are encoded that have no original image shared in common, then the output should be 0. And sort of, we in the back of our minds know, and I'm showing you up top, what the original images are that correspond to this encoded image. The function doesn't have access to this, but I'm just showing it here for clarity. And we'll notice that none of these images are the same, and so the function should return 0. On the other hand, if one of the images was shared between these 2 encodings, we would want this function to return 1. And so this is in some sense a similarity function, which is trying to tell us yes or no, do these 2 encoded images have an original image in common without ever seeing what the original images were. Now, why should you expect this something that you should ever be able to do? Well, the idea behind these encoded images is to be able to use them to go train some downstream machine learning model. These encoded images can't be completely noise, because if they were, you wouldn't be able to get any utility out of the models. So these encoded images have to have some resemblance to the original data sets. As humans, it looks like noise to us. But we already know machine learning models can train on these encoded images to get a useful classifier at the end. So we're going to abuse this fact in order to train a machine learning model to do something slightly different. And instead of training the model to do a useful task, we're going to train the model in order to predict this similarity. All right, so this is the first step. We have something here, but this is not doing reconstruction. So what do we do next? What we're now going to do is we're going to take this similarity function that will tell us when images, when encoded images have an original image shared in common. And what we're going to do is we're going to cluster together the entire training set, the encoded training set, and we're going to draw edges whenever 2 images shared an original image in common as computed by our function. Now, our function might have some errors. In practice, this function for us has something like 96% accuracy, but it makes mistakes some of the time, so it's not going to be perfect. So we'll run some kind of connected components algorithm in order to find all of the clusters, where all of the images in one cluster should share at least one original image in common. And then the second step in our attack is a fairly simple merge operation. We know that all of the images on the left here correspond to some original image, and we know that the way we got these encoded images was by a linear combination of original images. And so the standard thing you can do then, in order to average out the noise, is just to, again, put the images on top of each other and just compute the mean. And that doesn't perfectly give you the original image, but it gives you something that is more or less a recognizable version. And if you do some fancier math, then you can actually get basically a fairly high quality reconstruction of the original image. And then you can do the same thing for your set on the right, put them together, take the mean, do a little bit fancier math, and then you get another high quality reconstruction of what the image actually was. Okay, so how well does this actually work in practice, not just on these sort of twice of our 10 examples? So the InstaHide authors release a challenge on GitHub where they construct a data set, they encode the data set, they reveal the encodings to everyone, and then they say, like, try and solve this. And we can basically completely perfectly solve their challenge. So on the top here, what I'm showing is the original images that they encoded. And on the bottom is the reconstruction attack that we've done. And you'll notice that there are some differences between the original and the encoded extracted version that we have. But by and large, we have a fairly high quality reconstruction attack on this scheme. For example, you'll notice that in the rightmost figure, the fish that the man is holding is a little color distorted, but you can still completely tell what's going on in this image. And it's not just these 4 images, it's the entire data set we can reconstruct, and it works quite well. Okay, so this is the attack that we have on InstaHide. Now let me tell you about one other scheme, which the scheme behaves very, very differently, but the attack is going to work very similarly. And hopefully we'll be able to see some lessons for how to attack these kinds of schemes because of this. So what this scheme is called, is called NeuroCrypt. It was released, I don't know, 6-8 months ago now. And the idea behind this scheme is slightly different. InstaHide is designed to prevent extraction, but NeuroCrypt is designed to prevent what's called re-identification. So what's re-identification? What this means is that InstaHide is designed to just prevent you from being able to recover completely the image. NeuroCrypt is designed to make it hard, so that even if you knew what the original image was, it would be hard to match this with the encoding. So you can't even do this sort of matching thing. And the way to do this is that they have some kind of keyed function that goes forward. So whereas InstaHide had sort of anyone can compute forwards, with NeuroCrypt, you have to have the encryption key in order to go forwards. And moreover, if you have the encoded image, you can't go backwards. And so this is a stronger security guarantee, because you can see how if you can't even achieve identification, then clearly you can't achieve extraction. Because if you could extract, then all you would have to do to re-identify would be to extract the image and then compare which of the images on the left side was most similar. And so re-identification is a much stronger thing you would hope to be able to achieve. And so NeuroCrypt tries to achieve this. And we're going to show that it actually doesn't achieve this re-identification task. Okay, so how does NeuroCrypt work? It's going to work quite different. It's going to start by randomly initializing a neural network. This is any kind of neural network that you want, and we're going to give it random weights. Then what we're going to do is we're going to take this randomly initialized neural network, and we're going to apply it to the image, but not the entire image. We're going to take the image and we're going to split it into small patches. For CFAR10 images, maybe this means we just take 4 patches, but in general, for the large images that they consider in their data set, they split it into something like 100 different patches. And then they apply the neural network that's been randomly initialized to each of the 100 patches. And by doing this, they have somehow encoded each of the patches of the image with this random neural network that only they know and they're not going to release. So they take their neural network, they apply it to these patches, this gives us a bunch of encoded patches, and then they release these encoded patches along with the label. And now the question is, given this, is it safe? Is it safe to be able to release these encoded patches? Okay, again, there's a utility question. why is it that this is useful? Let's just take on faith that it happens to be useful. Let's try and understand the privacy again. Okay, so how are we going to attack this? We're going to try and do essentially the same flavor of attack on this scheme, even though the exact details of this scheme are very different than the details of this scheme for InstaHeight. And the reason why we're going to try and do a similar flavor of attack is hopefully this will give us some insights about the kinds of ways that we should be attacking these kinds of schemes. Okay, so let's go. Oh, my slides are frozen. Okay, there we go. So how do we attack NeuroCrypt? So what we're going to do is first ask how much signal is really lost. This is very similar to the question we asked for InstaHeight. Because in order to train a useful model, remember, we can't completely destroy the signal. If applying a random neural network to a patch of the image actually removed all of the signal, then this model would not be, it would not be possible to train actually good models on the resulting function that came out at the end. So there has to be signal still left. So the question is, how much signal is there left? And in order to measure this, what we're going to try and do is the following. We're going to start by training a similarity model that looks very similar to the InstaHeight challenge. We're going to sort of take our own data set of our own images, and we're going to construct a random neural network, and we're going to we're going to split them into patches, and then get the encodings with our neural networks, and then we're going to pair together the images with their corresponding encodings. And then we're going to try and train a function, just as before, that predicts that these are all correct because they came from the right sort of patches. The patches are aligned correctly. But if we had gotten it wrong, and if we had paired the encodings of the horse with the image of the car, and vice versa, then our function should return 0. And so again, we try and train this similarity function to operate on these encoded images because we know that these encodings are designed to be friendly for neural networks. And it turns out that when you try and train a neural network to do this, it can solve this task really, really well. Again, it can solve it to something like 95% accuracy. And from here, again, you can just directly use this model that we've trained in order to do the attack for us. So how do we do this in particular? All we're going to do is, let's suppose that I want to know if this image matches these encodings. I'm just going to say, okay, fine, I'll just pair them together, run the neural network on each of them, and this will give me a set of outputs. Some of them might be higher than others. I'll take the average and say the average is, roughly around 0.6, 0.7, and so I'll say this probably is the same image. On the other hand, if the average was instead around 0.1, 0.2, then probably the answer is no. And in particular, what I do is if I want to figure out this matching problem, this is the re-identification problem that they're trying to prevent, all I do is I construct the matrix, that's the n by n matrix, of all pairwise similarities, and then I just run a max weight matching algorithm, just a standard graph algorithm, to try and find the best assignment where I'm going to pick one entry from each of the rows and one entry from each of the columns to maximize the total sum. In this case, the solution happens to be this, but in general, this is sort of a known graph algorithm that will solve this for us. And we'll notice that it's important that you run this on the global scale because it actually helps find cases like on the bottom where we're picking a value of 0.2, which isn't the largest among all the things for the horse, but it's much better to pick this 0.2 because you can get some better costs for the other ones. Now, there are a couple of details for the scheme I'm glossing over. They have another permutation that's buried in here. But for the most part, this is how our attack is going to work. Again, the authors have a challenge that they post online. And again, we're able to completely solve this challenge with 100% re-identification accuracy. So the scheme does not sort of give this re-identification privacy that it hoped for. Okay. So brief conclusions then. The first conclusion is that when you generate these encodings, they have to be neural network friendly. Otherwise, there's no way that you would be able to use these encodings to train machine learning models, right? Like it would be nice if we could just encrypt them with AES or some other good encryption algorithm, but then there's no way that you could learn on them. They have to be some kind of neural network friendly output. But as a result of doing this, we can now use exactly this failure mode against itself to attack the models. The next lesson is sort of the title of the talk. Privately distributed training data seems like it's going to be hard. We didn't know this ahead of time. It could have been that this was an entirely valid solution that's very easy and we should just be doing right away. But for right now, at least, it looks like privately distributing training data in this way is something that's going to be difficult and require a lot of careful analysis in order to be able to achieve correctly. And so maybe the final lesson here is, at least for the time being, some combination of federated learning and multi-party computation and differential privacy is going to be the way forwards. It's not clear that this is going to be the way forwards forever, but at least for the time being, this is the best thing that we have. And so work that tries to improve this is very valuable because it sort of improves the best things we possibly have. And it's possible that at some point, someone will be able to come up with a scheme that allows us to reveal training data in some intelligent way. But for now, at least, we're not able to do this. Now, if you care, I think this is going to be really hard, in part because in our paper, we have some theoretical results. We worked with some cryptographers who wrote down some arguments that it might actually be impossible to do this to distribute training data in some, in some settings that cryptographers can reason about. But it's entirely possible you can make some set of assumptions that didn't make it impossible. So I'm not going to say it's impossible to do this task, but at least for now, it seems to be very hard. And so we should continue to be working on these kinds of federated learning, multi-party computation, and differential privacy in order to be able to achieve strong results without having to rely on these schemes which currently don't actually work that well. So with that, thank you very much, and I'm happy to take any questions.
Thanks, Nicholas, for interesting talk. I open to audience. Any question for Nicholas? You can open your mic or type in the chat.
Hi, I have a question.
Sure.
Yeah, very nice talk, by the way. I understand your basic idea, but there may be one concern, which is regulation. So it's possible that regulation, either from the government perspective or from the corporation perspective, forbid any travel of the data, transmission of the data out of the parameter of the local client. How would you convince the regulators that this is completely secure?
Yeah, no, this is a very good question. This is, yes, another challenge that I don't even touch on. Yeah, I think if we manage to get a scheme that worked, then it becomes a problem to understand if it happens to be like how we convince regulators. For right now, we don't have schemes that work. So I don't think it's necessary to think about how we would convince regulators that they do, because they don't even technically. But in the future, yeah, this would be a very good question. It's very easy to argue why MPC works. One of the hard things about privacy is that you can't release a data set and then later retract it. So if you release a data set that's been encoded in some way, this data set has to remain private essentially forever. And so it's very hard to make arguments that guarantee this. And so regulators might not want this to happen.
Okay, thank you.
Hello. I have thanks for this interesting talk.
Yep.
Yeah, for the re-identification part.
No, I think Muhammad, you sound a bit weak. Can you speak?
Hello.
Yeah, I can hear you.
Okay. Yep.
Yeah, so for the re-identification work, you assumed access to the original images, right? So may I ask, if you don't have access to the original images, is it possible to re-identify?
Yeah, okay. So just in case anyone couldn't hear, it was a little quiet. The question is, in the re-identification part, we assumed access to these original images in order to be able to compute this pairing. Is it possible to do the attack if we don't have access to the original images? And the answer here is no. But the reason why the answer is no is because we didn't try and do it in any other setting. The paper proposes, like their challenge that they post online, explicitly is asking you to do re-identification. And so we try and do re-identification. They also posed a second challenge on their leaderboard that had some technical problems, so we didn't try and solve that one. But the general sort of argument from this paper was that re-identification shouldn't be possible, and so we tried and we evaluated the papers on the threat models they were trying to prevent. And this one was the security argument in the paper was about re-identification, so we ran an attack for re-identification. It's not entirely clear if you would be able to do extraction. It might be easy, it might be hard. I haven't tried.
Okay, thank you so much. But I mean, for the sake of data privacy, assuming that the re-identification is not the main task, the privacy is the main task. So if you have this encoded image by this neural crypt, so far you cannot reconstruct the image without access to the original images, right?
Yeah, okay, so but like there are lots of things that I could do that preserve this. I could add Gaussian noise to the image, and now I can't recover the original. The question is, how much noise is enough, and when is it visually similar? And so the reason why NeuroCrypt wanted to move away from complete image reconstruction is to get away from all of these sort of fuzzy problems. And I completely agree that with them, that re-identification is the better challenge to try and solve. In cryptography, right, we don't try and design our encryption algorithms to prevent decryption. This is the end goal. We don't want decryption to be possible, but we design our encryption algorithms to be secure against things like indistinguishability against chosen plain text attacks. Because we understand that we should design our algorithms to be secure in the worst possible settings so that anyone can use them in any setting. And that's why I think NeuroCrypt is doing the right thing for trying to prevent re-identification, because if you can prevent re-identification, all other attacks fail as well. And so it's good that they're trying to prevent the hardest thing. It can't achieve that. It may achieve something less, but it also might not. In general, I tend to assume that if something is broken in the strong settings, it's probably also broken in the weaker settings. We just haven't put the effort into breaking it in the weaker settings.
Thank you so much. It's quite clear.
So any more question? Otherwise, we thank Nicholas for interesting talk. Thank you.
Thank you very much.
Thanks. So our next one is another oral presentation hosted by Zhang Le. Zhang Le is a professor from University of Electronic Science and Technology of China. Zhang Le, please.
Thanks, Cindy, for the introduction. I think next let's welcome Yu Ting He, Yiqiang Chen, Xiaodong Yang to introduce their work on class-wise adaptive self-destination for heterogeneous federated learning.
Okay, can you hear me?
Yeah, yes, please.
Let me see my screen. Hello, everyone. I'm He Yuting, a graduate student at the Institute of Computing Technology Chinese Academy of Science. Now I will present our work, class-wise adaptive self-distillation for heterogeneous federated learning. As we know, the local data in real world often exhibit non-identically distributed. When each client trains a local model on the biased data, its local objective may derive from the global objective and result in forgetting the global knowledge, which is the knowledge of previous training data from the other clients. In this paper, we'll focus on the label distribution non-ID challenge, where the period distribution PY varies across the clients. Our goal is to train a robust global model that can generalize well on the uniform distributed global test data. Here is the framework of field average. Previous methods solving the non-ID problem that can be divided into three phases: local training and global aggregation and local prediction. Recently, knowledge distillation has widely applied in FL. Some methods distill the knowledge from the instant or local models to a global model. The knowledge can be transferred from a neural network to another one by exchanging soft predictions instead of whole model parameters. Another line of work self-distill the global model's prediction during the local training to elevate the forgetting of the global knowledge. Our work is inspired by this idea. To elevate the forgetting, we are trying to answer the following question: how to learn a task without forgetting another one learned previously. An intuitive fix is to utilize the global model's prediction on local data to preserve it, like a FL-AAAI. But we've discovered that it is not appropriate to use a constant weight to control the distillation loss, because the ability of global model differs across the classes. Therefore, we design a class-wide weight to adaptively adjust the impact of the global model for each class during the local training. As shown in Figure 2, we observed that field average overfitting the local data and forgetting the global knowledge about the class 0 to 5. FL-AAAI avoids the forgetting problem, but it disproportionately harms the performance on the classes 7 to 9, where the global teacher model meets predictions. For this, our method, FedCast, utilizes the class-wide weight to help the local model adaptively control the impact of distillation based on the performance of the global model on each class. To present the proposed method, let me recap local self-knowledge distillation in FL first. Suppose client I is conducting the local training on its private data. There are two parts in the training objective. First one is the training loss, which is used to preserve the global view on the local data. As shown in equation 2, the knowledge of global teacher model is transferred a local student model. P and PG is the softmax probability of local and global model. Z and ZG is the output losses respectively. And the classification loss, LC, is the softmax cross-entropy loss between the local model probability and the one-hot ground truth labels. Then the overall loss is a weighted combination of two objectives as equation 4. As analyzed in motivation part, it's not appropriate to use a constant weight to control the distillation loss. So we design a class-wide weight. Then the question is how to decide the values for the class-wide weight alpha. And we know it is infeasible to attempt a grand search for it. So we establish a linear function between the confidence of a global model and the class-wide weight, using gamma and beta to decide the upper and lower bound of destination impact. And we use the actionary data to estimate the expectations. It is a small subset of samples of different classes, which can be acquired from the public dataset. Lastly, the framework of the proposed method is shown in Figure 3. In each computation round, the server estimates the weight alpha as equation 6, and the weight of each class is initialized to 1 in the first round. Then the server randomly samples a set of clans to participate and distribute the global model parameters and the class-wide weights to those clans. Each clan optimizes the overall objective shown in equation 5 and repeats the process until the global model converges. Let's move on the experimental results. For Cipher 10 and Cipher 100, we allocate a proportion of their samples of each class to each client according to directness distribution. And for FE-MINIST, we randomly divide and assign approximately 2,000 writers into 10 clients by default. As shown in Figure 4, the corner of each rectangle reflects the number of samples for a class on certain clients. This is the comparison accuracy on the benchmark dataset. Our method required fewer communication rounds to converge compared with the baseline method and achieved a higher final accuracy under all experimental settings. More specifically, our method outstands others at the local training stage, reflected by higher local accuracy. In conclusion, we sum up the main points of this work as follows. Discovered that the method based on self-destination can harm the performance on the classes where the global teacher model makes confident predictions. We proposed a class-wide self-destination method FedCat to adaptively soften the teacher influence for the classes where it is less reliable. We experimentally demonstrated that FedCat improves the classification accuracy, reduces the number of communication rounds, and speeds up the convergence. That's all. Thank you for listening. Do you have any questions?
Thanks. Is there any question from the audience? I have one question. So I realized that from your method, you need some auxiliary data to estimate the parameters, those alpha and beta. So do you have any experiments to show that? So how will the quality of this part of data will affect your final performance?
In our experimental, we randomly sample 32 samples of each class. It's a more small subset of each class, and so we can the class maybe upload it into server. If maybe the and in real world data sets, there are some public data sets in we can use.
So you mean you need to split some of your training data into this accelerated data set, then you estimate the parameters on that part of data, right?
I'm not. Okay. Yes.
So I mean, you have your training data and use part of the training data to estimate those parameters.
Yeah.
Okay. Thanks. Is there any other questions? Okay, if there's no questions, thanks. Thanks. And then the next will come Jia Chan trying to introduce their work on federated unsupervised clustering with generative models.
Excuse me, I am the presenter here, and I told the admin that I can present live. So
okay. Yep.
Okay, can you hear me and can you see my screen?
Yeah, yes, please.
Okay, thanks. Hi, I'm Jishan Zhang, and I'll talk about our work on federated unsupervised clustering with generative models. This is the work advised by Professor Kannan Ramchandran and Professor Kang Lee. So we consider the clustering problem in the federated learning environment. The application of this clustering problem includes providing relevant information to such as advertisements according to the cluster information, or improving the learning quality of the downstream machine learning tasks. For example, we can think of for the next word prediction task, we can prioritize words that are relevant to the topics other than others. So our main focus is clustering unsupervised, which is unlabeled, unsupervised data sets in the federated setting. A baseline approach that we consider to this problem is K-Fed algorithm. This is an algorithm based on K-means. So the first step they do is the algorithm first runs K-means algorithm at each local machine, and the server gathers and clusters the local centroids that are computed from each local machines. And lastly, local data points are clustered according to the centroids cluster information. The limitation of this approach will be that the clustering performance will be upper bounded by K-means algorithms performance. So to do better than the K-means, we can consider DNN-based clustering approaches. So another baseline approach that we consider is DNN classifier-based clustering models. There are many successful methods in this category for the centralized settings, such as ClusterGAN and Deep Cluster. So one natural approach is to train these models in the federated setting using federated averaging algorithm. However, the model training can become problematic when the client data is given given in heterogeneous manner, due to using federated averaging algorithm and having like gradient diverging problem, making this failed training at these cases. So what we use is, there's a recent work called IFCA, the Iterative Federated Clustering Algorithm, that clusters well for the heterogeneous client case. What they do is the algorithm trains multiple machine learning models that captures each cluster. The cluster is identified by comparing the model loss, and each model is trained using each cluster's local data and averaged at the server. The paper shows a good clustering performance for the supervised data sets using classifiers as the machine learning models that captures each cluster. So our question is like, how can we apply this algorithm to unsupervised data sets? And our answer to this problem is to use generative models. We consider likelihood-based generative models to be used with this IFCA algorithm. In particular, we are using normalizing flow models These normalizing flow models are invertible functions that maps the samples to some prior distributions such as Gaussians. The model is optimized to maximize the log likelihood of the training data. So basically capturing the training data's distribution. So in our case, each flow model will be optimized to give like high likelihood for each cluster's data, basically capturing the cluster's data's distribution. So for the experiments, we test our algorithm for a different level of client heterogeneity. Here, P0 refers to the IID distribution, and P1 refers to the case where each client holds only one cluster's data. And we report the cluster purity for measuring the performance. For our synthetic experiments, we consider Gaussian and subspace cluster data sets. We observed that our method is able to successfully recover the cluster across different heterogeneity levels. The plot on the right shows the cluster purity measured at each iteration of our algorithm for the Gaussian clusters case. And we observed that the cluster purity gradually increases over iterations with overall faster increase for the high heterogeneity case, P1 case. For the MNIST experiments, we test our algorithm with 3 different cluster cases. For the first is rotated. We generate a data set with 4 clusters by rotating the digit images by 90 degrees. And for digits, we run the cluster algorithm and compare with the ground truth labels. For the representations, we cluster the feature embeddings learned from a rotation prediction self-supervision task. This is result table for the cluster accuracy for each case. Our method currently does not work well for clustering the raw images, that is the clustering by rotation and clustering by digits. But for clustering the representations, our method performs better than the baseline algorithm in most cases. And also we find that our method can further be improved by using the baselines, which here is KFED, using the KFED's resulting cluster assignment as our initial cluster assignment. Okay, so since our current setup is having bad convergence for the clustering raw images, so improving this case will be our immediate next step. We also look forward to apply this method to like mixed IID, non-IID distribution case, and also generalize our method to different data sets as well for like CIFAR, MissionNet, and NLP data sets. Okay, thanks for listening.
Okay, thanks for the introduction. Is there any questions? I have one question regarding your experiments. I read from your slides that you have 3 scenarios. The first one is P equals to 0, and P equals to 0.5, and P equals to 1. You have 3 figures, I think, in the previous slides. I think yes, this one. So actually P1, P equals to 1.0. So you mean each client will have only the data from only one cluster?
Yes, correct, yeah.
So in this case, if you do clustering on each of the local clients, then it will just return you just one center of those samples. So how can you guarantee that your model will convert to class all those samples in 3 clusters?
Okay, so your question is how do we know that this can, like running for P1 case, our algorithm will converge to capturing each of the cluster?
Yes.
So what happens is that what they do is they first assign the cluster based on the model loss and improve the model with the cluster model, and how they train across the client is that they run a federated averaging algorithm, which will be basically doing the weighted average over the updated models, and this weight will be This way will be related to the number of number of data points that in that cluster. So what happens in here is that eventually one model will capture like majority of the data point, and this will again increase the increase the data that is captured in one client over the iterations, and as doing that, the other models that are capturing other clusters will have very small weight due to like having small number of data in that in the first cluster. So this naturally gets out it ends up with capturing one client's case.
So do you have any theoretical analysis on the convergence of your method?
What kind? Sorry, which analysis?
Theoretical analysis on the convergence of your method.
We don't have the theoretical analysis, but I think theoretical analysis is kind of provided in this original work of this iterative clustering algorithm. Yeah.
Okay, thanks. Is there any other questions? Okay, thanks, Jonathan Chuan.
Thank you.
I think next will come Haizhou Shi to introduce their work on towards communication efficiency and privacy prevention, preserving federated representation learning.
Okay, can you guys hear me?
Yes, please.
Yeah, okay, cool. I'll share my screen. Can you guys see my screen? Okay, hello everyone. My name is Haizhou Shi. It's a great honor for me to be here and present our recent work towards communication efficient and privacy preserving federated representation learning. And this work is supported by OPPO Research Institute, and I'm from Zhejiang University. So in the next couple of minutes, I'm going to first talk about the background of the federated representation learning, and then I will discuss some of the observations that we make in terms of applying the self-supervised contrastive learning technique in the federated scenario. And then I'm going to present our work that typically leverages the observation that we make. So nowadays, the typical representation learning framework is deployed at a data center where there are tons of publicly available data collected by the crowdsourcing workers or from other multiple sources. So popular frameworks like SimClear or Malco leverage about 1 million to 10 million data samples in total to train their network. And we already consider this amount of data is super huge and computationally expensive. However, when you consider a large network of edge devices, for example, let's consider a mobile phone manufacturer which possesses a network of 10 million to 1 million users. The story is even more overwhelming. Well, let's suppose a user on average takes 10 to 100 photos per month. Then we're talking about 1 billion to 10 billion samples in total generated by all the users. Besides, these kind of data are never cleaned and they don't have any labels. So how can we efficiently utilize these huge amounts of data in a distributed federated system is a problem that worth addressing. So a typical federated learning system is comprised of 2 stages in a single communication round. The first stage is local training, during which the model is trained on the client side with the private data the user collected. If we regard supervised learning as a special form of representation learning, then we can roughly divide the local training into 2 categories. The first one trains the model under the guidance of the labels, and the second one is trained without the labels. And the second stage of the communication round is global aggregation, during which the client sends back their locally trained models to the server, if there is any, and the server aggregates the client's models and then redistribute back to the clients. There are also 2 main categories of global aggregation. The first one is based on the weight averaging, such as fat average, as we are already familiar with. It means actually we simply average the weights of the models, but it requires the client have the same model architecture, and is also of a high risk of privacy leakage since the clients expose their local models to the server or to the peers. Well, the second one is the distillation-based method, which leverages only the logics or the predictions of the local models for the global aggregation. Well, since there are two types of local training and two types of global aggregation, we can now have four types of federated learning frameworks by combining them arbitrarily. The first type is weight averaging-based supervised federated learning, for example, FedAverage, FedProx. And second type is the distillation-based supervised federated learning frameworks, for example, FedDF and FedMD. And the third type is the recently really popular FURL frameworks, which stands for the Federated Unsupervised Representation Learning Frameworks. For example, we have FedC and FedU. And the fourth type is our ambition is to achieve the fourth type in this work. But before diving into the details of the framework that we proposed, we would like to share one important observation that we make when we apply the technique of self-supervised learning in a federated scenario. Here in the slides, we perform only local training without any global aggregation. And we compare the performances of the supervised learning and self-supervised learning along the changes of the non-IIDness. Here, as you can see, when the alpha value decreases, the data distribution of the clients are more diverse. And as we can see in the figure, when the alpha value decreases, the performance of the self-supervised learning drops only a little bit. However, in contrast, the supervised learning has a much larger performance gap. And even in some extreme cases, the local training of supervised learning is completely corrupted. However, the self-supervised learning is much robust. So we name this property of self-supervised learning as the robustness against the statistical heterogeneity. Now, as a natural question following this property is that, what does it mean for the federated learning framework, and how can we utilize this robustness? And now, since the local training is much more robust against the non-IIDness, we can actually perform the local training for longer epochs. And it in turn decreases the communication rounds of an FL system. But can the weight averaging based methods utilize this advantage? Of course, the clear answer is no, because although the representation space of the self-supervised learning method will converge to a better spot under longer training, the parameter space of each client model will eventually diverge. Directly averaging these diverged models will not give you anything meaningful. Therefore, we need to design a method that directly works on representation space to utilize this robustness of self-supervised local training. Here we propose a new framework called FLEST, which stands for Federated Learning with Ensemble Similarity Distillation. So here's how FLEST works. At each communication round, the client model will be trained locally with data under the self-supervised control paradigm, such as SimClear or Moco. And then each client model will infer a similarity matrix on the public data set. What we are assuming here is that we assume that the similarity matrix captures the knowledge of the locally trained model. And by transferring this similarity matrix instead of model weights, we decreases the risk of the privacy leakage. And finally, the server ensembles the inferred similarity matrices into one learning target, and then use this learning target as an offline teacher to actually distill. Oh, there's something wrong with my PowerPoint. I'm sorry for that. So let me reopen it. Sorry for that. Okay, can you guys see my screen? Yeah. okay, here we are. So we use this target similarity matrix as the offline teacher to distill a student network. And then after the distillation is done, the server will redistribute the model back to each client. So we then benchmarked our proposed method on 4 different data sets and yielded a promising result. Our new federated learning framework, FLAST, performs comparably as the baseline's Fed average, but is more privacy preserving and communication efficient. What's more, it potentially supports the model heterogeneity, which means the client model can now have different architectures. And as we can see, in some extreme cases where the communication round is strictly restricted to a very small number, as you can see in the middle sub-figure here. So our framework FLAST outperforms the baseline by a very large margin, which also showcases that our method utilized the property of the robust local training better than the weight averaging based method. And we also benchmarked the convergence property of our method by empirical experiments. Here we can see that the convergence upper bound is actually looser than the Fed average. It might be caused by the fact that our method works on the representation space rather than the parameter space, which creates some sort of difficulty for the model convergence. Well, actually how FLAST performs theoretically is one of the important works that we need to investigate in the future. And thanks for listening.
Thanks for the introduction. Is there any questions?
Hey, hello. Hi, Joe. I have a question about the public data set you used for ensembling. So what's the ratio between the local private data and the public data? So how can the operating user to turn this hyperparameter?
Actually, we test different size of the public data. Now, in the main experiment we showed here, actually the size of the public data set is the same as the local data set that each client has. However, we also observed that if we increase the public data set size, the model can actually have a better performance. And also we test the properties of this public data set to see how this data set influences the performance in terms of the domain, its own domain compared to the client's data domain. Actually, when the public data set is out of domain, for example, they have very different classes, the performance is actually degraded, which is also an important question that we need to conquer in the future. Yeah.
Yeah, because
thank you for the question.
Yeah, because in practice we cannot control this ratio for public data set, right? Because it makes more resource to collect this public data set. Yeah.
Yeah. But I think what we can do here, if you can actually deploy a public data set on the cloud side and also let the user to download this public data set. Yeah, I think that's something that we can definitely do in real life.
Mm-hmm. Okay, thank you.
Yeah, thank you.
I have one question. So I think in your framework, you have for each of the client, you will have one similarity matrix, right? And on the server, you have to combine all those similarity matrix and to do those knowledge distillation, right?
Yeah. Yeah.
So how do you combine all those matrices? You just average them, or you have some advanced method to process this?
Yeah, actually, what we did here is that simply averaging that will cause too much noises to this learning target, because when the non-ID is extreme, some client may have a very good representation power for certain kind of classes. So what we did here is that we first did a very soft max it with a very low temperature, which means we actually filter out those noises, and we only keep the similarities with very large value, which means the model is very confident that these two samples are similar. So after that, we then average that as the learning target. Yeah, Thank you for the question.
Another question. So do you have any plan to release your implementations of this work? Because I think this is very interesting.
Yeah, actually, I'm doing the code reorganizing here because there are some it's definitely not the perfect status to release the code. I'm still working on that. Yeah, probably soon. Yeah.
Okay, thanks.
Yeah, thank you.
Okay, if there's no any other questions, let's thanks the authors and then welcome the next author to present their work. Okay, so next we will have the author of Harmid Fadari to introduce their work on robust federated learning by training on parameter ranks.
Hello, can you see my screen?
Yes, I can see the screen, but it's blank.
Oh. Oh, something happened. Oh, can you hear me?
Yes, we can hear you.
Oh, my screen is frozen. Oh, okay, now it's okay. Hello, everyone. I'm Hamid Muzaffari, and my presentation is about designing robust federated learning by training on parameter ranks. And this is a joint work with Virat and my advisor, Amir Humansad from University of Massachusetts, Amherst. Probably you saw this first slides a lot, but federated learning allows mutually untrusted clients to collaborate to train a machine learning model together. And in one of the most basic versions, we have FedAverage, that we have different clients, and each one of them, they have their own objective functions, and they try to reduce the loss based on their local data. So our objective is find a common model that works well on average for all the clients. And because we are training on untrusted clients, FL is very susceptible to poisoning attacks. And one of the most destructive versions of these poisoning attacks is untargeted attack, where the adversary's goal is to destroy the performance of the global model for the test data. Let's talk about the intuition of the poisoning attacks. So first, we have the FedAverage that it doesn't have any security mechanism. So let's assume that in this picture, we have the space of the possible updates. Each client is sending the model updates of their network to the server. So each update is consisting of n parameter weights. So each parameter weight could be a float of 32 bits or 64 bits. And the server collect all of these model updates, aggregate them, and announce the global model for the next round. So because the FedAverage doesn't have any security mechanism, it's very easy to attack it. And even one malicious client can destroy completely the global model. So the adversary just crafts the malicious updates to maximize the distance between the benign and malicious aggregations. And a recent work shows that even one client can destroy the model totally. Some recent works, they try to introduce Byzantine robust aggregation rules, and their goal is to shrink the space of the accepted updates. So they define a safe zone, and such as a multi-chrome or tree mean, and they are just picking the updates that they are in this safe zone. So now the hands of the adversary is a little bit tied. But the adversary change is a strategy. Now we have new papers that they are aggregation rule tailored poisoning attacks. They try to find malicious updates by solving an optimization problem of reducing the performance of the global model, and at the same time keeping the update in the safe zone. To address and defend against untargeted attacks, we designed FSL, or Federated Supermask Learning, and our intuition was we should make the space of the accepted updates sparser. So we are trying to reduce the adversaries' choices. So in current setting, each update consists of n parameter weights, and these parameter weights, they are continuous, they are float numbers. So we are shifting to a new setting that the clients, instead of the training weights, they are training ranks. So it's like a space of the discrete updates. So each update is a ranking from 1 to n, which n is the size of the network. So in FSL, instead of asking the clients to train weights, we ask clients to rank the edges in a random neural network. So it's model parameter weight against ranking. FSL provides two main features. The first one is robustness, and as a side feature, it also reduces the communication cost too. So what is a supermask? Supermask was introduced first in NeurIPS 19 by Jude, that they tried to find a subnetwork in a randomly initialized network without any training. And they introduced supermask as a binary mask of zeros and ones that can be superimposed on the random neural network to obtain a final subnetwork. For example, we have here on the left a network of 6 edges. So all of them are randomly initialized, and we can find a supermask that just produces a subnetwork of half size of the original network. For training supermask, one of the algorithm is edge pop-up. This edge pop-up, we assign a score to each edge in the network. We train on the data, and we find the best edges to minimize the loss. If adding an edge to the subnetwork increase the loss, we reduce the score of that edge. So now how FSL works. In the first round, the FSL server pick a seed and produce random weights and random scores. And then this FSL server announce this seed to all of the clients, so the clients can reconstruct the random weights and random scores. The most important part is that the weights and the scores remain fixed throughout all of the learning. So we are not changing the scores, or we are not changing the weights. We are just trying to find the best global ranking of these edges. And another job of the FSL server is to broadcast the global ranking of each round. In the phase of training, the clients receive a global ranking. They reorder their edges based on the ranking. They use this edge pop-up training method to train, and they find the importance of the edges in the network, and they produce a ranking from least important to most important. For example, here we have 3 clients, and we ask them to rank the random edges in the network from the least to most important, and produce a subnetwork of half of the original network. So for example, client 1 found this local ranking that the edge 4 is the least important and edge 1 is the most important part. And we have other local rankings too. Now, in each training round, after finding the local ranking, the clients send their local ranking to the server, and it's one of the job of the server is to collect all of the local rankings and aggregate all of them into one global ranking. For rank aggregation, the server assigns a reputation for each vote and sums all of the reputation and again sort them to find the global ranking of the next round. So based on the 3 local ranking of the previous page, the server produced the global ranking for the next round. And this goes on to find a global ranking after a specific number of rounds. So let's talk about the features of the FSL and some experiments. So the main feature of the FSL is providing robustness. So we did experiments on 3 different data sets, MNIST, C410, and FE-MNIST, with large number of users, like 1,000 clients for MNIST and C410, and 3,400 for FE-MNIST. And we distribute the data sets using Dirichlet in a non-IID fashion. And we compare our method with well-known Byzantine robust aggregation rules such as trim mean and multi-chrome, and one of the quantization methods such as SIN-SGD for different percentage of the malicious attackers. So as you can see, for example, for C410, FSL provides better performance in case of, for example, having 10% of the clients being malicious or 20% of them being malicious. So as I said, a side benefit of FSL is reducing communication costs too, because instead of exchanging weight parameters, we are exchanging rankings. Clients upload their local rankings and download the global ranking for the next round. So because of that, we are reducing the communication costs of 32 n bits if we assume n is the number of parameters in the network and each one of them is encoded with 32 bits, to n log n bits for each layer. N is the size of the layers. And as I said, FSL can provide similar performance as Fed-average. For example, on experiments on C410 that we distributed them non-IID over 1,000 clients, we achieved similar performance as Fed-average, 85%, with a very small network of convolutional layers. And we achieved this accuracy while reducing the communication costs by 35%. And also we compare our method with compression techniques in federated learning, such as SIN-SGD, which is a quantization method, and TopK, which is a sparsification method. We show that our design can provide similar or better performance, and also reducing the communication costs similar to them. But our main goal was providing robustness, and the communication cost is just a side benefit because of the exchanging the rankings. So thank you, and if please look at the full paper on the archive.
Thanks. Is there any questions from the audience? Okay, if there's no questions, so let's thanks the authors again, and let's welcome the next author.
Thank you.
Thanks. Next, we will have Wang Yujia to present their work on communication compressed adaptive gradient method for distributed non-convex optimization.
Okay, can you hear me?
Yes, please.
And can you see the screen?
Yes.
Okay, thank you. And thank you for introduction. Hello, everyone. This is Yujia Wang from Penn State University. I will be presenting our work, Communication Compressed Adaptive Gradient Method for Distributed Non-Convex Optimization. This is a joint work with Lu Ling from UVA and my advisor, Professor Jinhui Chen. So distributed learning has been widely used in training large-scale machine learning problems. However, the communication costs between the server and workers is still a major bottleneck for distributed learning due to large number of workers, large number of model parameters, and the limited bandwidth for transmissions. The traditional machine learning problems can be formalized as a minimization of a non-convex loss function f, while the objective function for distributed learning is then a minimization of aggregated non-convex loss functions on each participating worker. Here n denotes the total number of workers, and fi is the non-convex loss function on worker I. There are several algorithms for solving the traditional machine learning objective function. Stochastic gradient descent is simple, but it is slow to converge when facing some heavy tail stochastic gradient noise. M-squared is one of the famous adaptive gradient methods with the moving average MT and the maximum of existing moving average VT. It is stable and empirically more efficient than SGD in training large-scale language models. There are two principal ways to reduce communication costs. One is reducing communication bits per round, and another one is reducing the communication rounds. The gradient compression is then an effective way to reduce the communication bits. Here is the assumption for biased compressors. The canonical examples for biased compressors are top K and scale sign compressor. The top K compressor is more intuitive, so here we provide the definition of scale sign compressor. Existing solutions to reduce communication bits are mainly based on applying gradient compression strategy to distributed SGD. The naive compression for distributed SGD is straightforward, but can diverge even in simple quadratic problems. Error feedback is then developed with and widely used with convergence guarantee. It introduces a compensating error sequence delta T to correct the compression error in previous steps. Since gradient compression with error feedback successfully reduced the communication costs in distributed SGD, so can we apply the error feedback to adaptive gradient methods? Here we denote GT and GT hat as the fresh and compressed gradient. And if we use error feedback, delta T is then the error sequence. So the updating rule for variance term VT plus 1 of M squared is formalized as follows. We can see that previous work claims that VT can be unstable when applying error feedback, since the compression error here holds the quadratic term of compression error difference, delta T minus 1 minus delta T squared, while the error feedback only guarantees a constant bound for delta T. So the accumulating compression error makes the VT unstable. Markov compression sequence provides a solution to the unstable of variance term VT. It is recursively defined as follows, with a biased compressor C and a sequence of original vectors W. The advantage of Markov compression is that the compression error can be largely reduced if the underlying sequence WT is convergent. And the compression error is directly controlled by the difference of the original sequence. So if WT is convergent, Markov compression error at the T step will be much smaller than the constant error bound obtained by error feedback. We adopt Markov compression to fresh gradient. That is, on each worker, we compress the difference between the fresh gradient from the current step GT and the compressed one from the last step GT minus 1, GT hat minus 1. And we send this compressed sequence to the server. However, the server needs to broadcast the full model xt plus 1 after updating. And this also results in high communication overhead. To further reduce the communication costs, we consider worker-side model update with two-way compression. That is, the server sends a Markov compressed gradient difference to the worker as well. So therefore, our CD item can be summarized as follows. So at the Tth iteration, the worker I computes the fresh gradient with a batch size tau, and compresses and sends the gradient difference CTI, updates the local Markov sequence GT hat, and the server updates the Markov sequence GT hat locally as well, build another compressed sequence CT, and send it to workers for the worker side updates. The worker I then updates and uses gtilde, which is also a Markov sequence. Use this to update the momentum, the variance, the v-hat, and update the model via M-squared optimizer. We emphasize that only the compressed gradient difference, CTI and CT, are transmitted between the server and workers. So therefore, our CD-ADAM is indeed communication efficient. It reduces the communication bits during transmission. For example, for the scale sign compressor, CD-ADAM only takes 1 bit instead of 32 bits per dimension in each communication round. Here's an example showing the comparison of training loss and test accuracy against the communication bits of training ResNet 18 model on CFAR10 dataset. Our proposed method achieves around 32 times communication cost improvement over the original M-squared and around 5 times over 1-bit ADAM. And we conduct the convergence analysis for our proposed CD-ADAM with another 3 common assumptions about smoothness, bounded gradient, and bounded local variance. The theoretical convergence result shows that our CD-ADAM reaches the epsilon stationary point with the order of 1/epsilon² iterations. And this result matches the iteration complexity of standard M-squared without compression. Empirical experiments on non-convex logistic regression problems on several data sets and the experiments on various deep learning models on CFAR10 dataset back up our theory. And for more theoretical and experimental results, please refer to our paper. And thank you all for your attention. Any questions?
Any questions? If there's no questions, thanks, Wang Yujia. Thanks for your introduction.
Okay, thank you.
Next, let's welcome the authors to introduce their work on COMFISH, Federated Learning for Large Networks on Memory-Constrained Client-Side Scheduling.
All right, can you hear me?
Yes, please.
Great. All right. Okay, I'd like to thank the organizing committee and the chair of this session. Today, I will be presenting COMFETCH, Federated Learning of Large Networks on Memory-Constrained Clients via Sketching. This is a joint work with Brendan Fung, Yifan Yang, Arjun Rajkumar, Amitabh Varshni, and my advisor, Farang Wong. And together, we are representing the University of Maryland at College Park. Okay, so this is a simple diagram of a centralized federated learning model, as we've all seen many times today. So when we look at this process, local update and uplink communication complexity has been addressed through a series of very clever algorithms such as fetch HCD, fedcomgate, VRLHCD, scaffold, etc. But there hasn't been too much work in recent literature addressing download communication and local memory complexity. And what I mean by this is hosting a model that is transmitted from a central server. So the question we wanted to answer is, can low fidelity clients train a massive architecture without hosting the entirety of all of its parameters? If we assume we're in an Internet of Things paradigm and our client does not have a large memory capacity, then hosting a large model such as a wide ResNet, for example, or a transformer model may be exceedingly difficult. So the solution we approach this problem with is a classical dimensionality reduction technique known as sketching. And within sketching, we use the count sketch data structure. So without going into extreme technical detail, count sketches are structures which essentially hash entries of an n-dimensional vector by essentially pooling randomly selected entries together over C buckets. So C here is referred to as the sketching length. And then the nice thing about count sketches is that they have a sparse matrix representation, which corresponds to the hash function that is associated with it. So the way count sketches work is you basically combine a uniformly drawn hash function point-wise with a sign function. So as an example here, we have a count sketch matrix being applied to a length 6 vector. Essentially what you see here is that the entries of this vector are pulled together additively and subtractively over a specified number of buckets. So in this case, C is going to be equal to 3. Okay. And a really nice property of count sketches is that they're unitary in expectation. So we can apply a matrix multiplication by the orthogonal of the count sketch matrix, and what we should get an expectation is the vector. Okay, and we're going to exploit this property. Okay, so previously we were talking about count sketches in the context of dimensionally reducing vectors, but it turns out you can actually extend this scheme over to higher dimensional tensors, such as matrices, or even higher order than that. We won't go into the details of how that works, but this is basically how we will compress model parameters in a neural network architecture, such as feed-forward MLPs and convolutional networks. So just a quick overview of this paradigm. So here x superscripted by L-1 represents the output from the L-1th layer being fed into the next weight parameter. So basically what happens here is that this weight parameter has been shrunken by a sketching matrix H. And then to restore it, all you would do is apply the orthogonal of H to it. So if you look at the full forward pass through this particular layer before it passes through the nonlinearity, what happens is it gets fed through HW, and then we just apply H transpose to it. And then what you should notice here is that because of the properties of that expectation we discussed earlier, H transpose H times W should roughly be equal to W. And there are some guarantees associated with that, which are probabilistic in nature, which I won't go into here. But the important thing to note is that it will roughly be the original weight matrix. Okay. So then how does the actual protocol work? So the protocol we have referred to as ConfEtch works like this. So instead of transmitting the entire weight matrix, the central server transmits these parameterized weight pairs. And what goes into these pairs is essentially each weight parameter shrunken by the count sketch matrix, and then essentially the transpose as a count sketch matrix. Okay, so this is actually cheaper to transmit than the entirety of the weight matrix itself. And once you have these pairs, then you can effectively restore W, or at least restore it to an approximation of itself. So basically what happens is the central server transmit these pairs, and then the forward pass proceeds as usual. And then within the layer, you're going to restore this count sketch weight matrix by applying the transpose of the count sketch matrix to it. And then the forward pass proceeds as normals. And then essentially the client is going to send back gradients with respect to the with respect to the sketched weight parameters, not with respect to the entirety of the weight parameter. So if we wanted to go over a high-level summary of all these transmission, upload, and computational costs, so in a naive setting, transmission of a weight parameter is going to be, if we assume the weights here are square, is going to be big O of n squared, but by transmitting these parameterized pairs, we can essentially reduce this transmission cost, assuming that C plus 1 is less than n. Okay, and then as for gradient uploads, in the naive case, in the unsketched case, it's going to be O of n squared, but in our protocol, it's going to be n times C. So as you can see here, these communication complexities are going to be very dependent on the sketched dimension length that is chosen. And then as for computational complexity, In the unsketched case, it's big O of n squared, whereas in the sketch case, it's a big O of n c. So you might be wondering then, how aggressive can we get with the sketch parameter C? The lower you go with C, the more aggressive you get with it. The less likely your unsketched version of your weight is going to resemble the ground truth weight itself. Okay, so there's this trade-off there. Okay, and then we have many results in our paper, but this is just a sample set of results of this protocol in action. In the actual paper, we compare ourselves against other algorithms which try to reduce communication complexity, mostly on the uplink end, which involves sketching gradients or trying to compress the computational complexity of local updates involved. But as you can see here, in a CFAR10 classification test using a simple 9-layer ResNet, we can get quite aggressive with compression without sacrificing a lot of test accuracy performance. Okay, and then for more details, I encourage you to look at our paper that's on the archive. So thank you.
Okay, any other questions? Okay, if there's no questions.
I have a special question. You calculate the communication cost, but do you have a experience about the memory cost?
Right. So the communication cost reflects basically how much it's going to transmit those sketched weights. That's actually just going to correspond to the memory cost itself, because all you're storing are those parameterized weight pairs. So essentially, there's just a one-to-one correspondence between that download cost and the local memory cost. So they're related in that way. But thanks, yeah, that's a good question.
Thank you.
Are there any other questions? So if there's no questions, let's thank the authors. And I think this is the end of this oral section.
Okay, thanks, Zhang Le, to hold this session. I think we go to our next session. Let me share the screen first. Hi. I think our next session is we will, on behalf of the work community, I'm happy to announce best research paper, best student paper, and best application paper. The best research paper is the FL-AAAI. It's a tackling labor deficiency in federated learning via personalized self-supervision. This paper actually proposed self-supervised learning framework with a series of algorithms to tackle two challenges in FL. It's a data heterogeneity and labor deficiency. The paper author is Chaoyang He, Zhenyi Yang, Alan Mustard, Sang-Woo Lee, and Maudi Sotono Kotabi, and Saman Advertisement. They contribute to the author for this base research paper. We might invite this award recipient. Maybe you want to say some work to this winning paper. Probably ask Chaoyang He. Yeah.
Oh, hello everyone. Thank you for this recommendation. Actually, I think this paper, maybe we are not the first one doing this, but we are the first one think about it, how to land this kind of techniques in real-world system, especially our FedMS setup. So hopefully we can further enhance this platform and share the results to the AI community. Thank you very much.
Thanks, Chaoyang. Okay.
Thank you.
So our next base student paper is the GEAR, the margin-based federated training approach. I think the paper proposed a GEAR to tackle the problem on adversarial robustness in federated learning. The GEAR can maintain both natural accuracy and robust accuracy in the federated learning. The paper author is Chen Chen, Jie Zhang, and Lin Juanyi. Maybe we can invite Chen Chen or either Lin Juanyi to speak some word for your paper.
Well, I'm very happy to receive such a reward. And firstly, I want to thank my collaborators, Jie Zhang and Lin Juanyi. I also want to thank the reviewers for giving me advices. Actually, they also helped me a lot for revising the paper. Of course, I also want to thank the organizer for holding such amazing workshops. And yeah, thank all of you.
Okay, I think Chen Chen. I think last but not least, right, the base application paper is the WT Shapley, Efficient and Effective Incentive Mechanism in Federated Learning. I think the paper proposed FL Federated Learning Framework, the leverage the WT Shapley, and adopt the end-to-end mechanism based on the WT Shapley to enable several natural gas companies from different cities to train an object jointly detection computer vision deep learning model to identify potential hazards. I think the paper author is the Chen Yiyang, Jie Liu, Hao Sun, Tong Zili, and Zheng Xiang Li. Maybe we can invite, Chen Xi, Chen Yi, or maybe Zheng Xiang. You want to speak a few words about your paper?
Okay, thanks, Adrian. This is Zheng Xiang. Yeah, I'm from EN Group Digital Research Institute. Thanks a lot for the workshop organization and the community. We do enjoy the invited talks and the informative presentations today. As one of the biggest natural gas distributors in China, EN serves about 20 million families in China and 180,000 industry companies with annual revenue above 116 billion Chinese yuan. So as a research institute in EN Group, we facilitate the digitalizations, transformations of EN Group with 4 listed companies. Since 2019, we have continuously worked on federated learning with the support of real-world applications, including energy consumption forecasting, machine learning predictive maintenance, and safety inspections mentioned in today's paper. So we are very excited to learn new technologies presented today. We hope we can adapt some of them and related to our real-world applications. So besides the data privacy, we are extremely interested in incentive mechanisms and fairness of federated learnings to establish the federated learning ecosystems, and thus we can push the industry digitalizations and AI forward. So this paper, WT Shapley, is one of our work along these directions. We was inspired by Prof. Yi Han's work, which evaluate the participants' contributions using Shapley value. So it's quite effective, especially combined with our domain knowledges in our home facility safety inspections applications. It can encourage contribute some scarce but very important data to improve our model quickly. So we are very grateful to receive these best applications award. Thanks again to the workshop organizers, and thanks to all for your attentions.
Let us to congratulate to all the reading paper author for their outstanding FL work. So on behalf of the organization committee, I would like to deliver this closing remark on this success of our international workshop on trustable, verifiable, auditable federated learning in conjunction with AAAI. We held virtually due to the condition generated by COVID-19. I think I want to congratulate committee to successfully host the event, such as the invited talk session. All presentation were delivered with minimum technical issue. I believe that during this half-day workshop, we all have the insightful, interactive discussion and great chance to share the outcome of our research. Finally, I'd like to thank all our distinguished keynote speakers who shared their valuable experience at the invite talk section. all the presenter, all the author, reviewer, and all the party who will contribute their best effort and assisting in organizing the event and ensuring success of this workshop. I do hope this FL workshop is able to impact all of us to greatly foster and empower the society through the science technology from the FL innovation. Jenny reminder, all accepted papers in this workshop will be invited to submit to the special issue of IEEE transaction on big data. Please keep in mind, we still have the various sessions afterward, like virtual poster session, networking in gather.town. Please do enjoy the rest of the conference. To conclude, thank you for the great contribution and looking forward to seeing you in coming conferences. So I pass back to Professor Yi. Yeah.
Okay, thank you very much, Singi. Thank you everyone for taking part in our workshop. As Singi have mentioned just now, we now conclude our Zoom session here. And if you have access to the virtual gather-town, we still have posters lined up there, so you can interact with the poster presenters and also enjoy the remaining time for networking. I think ours is the last program for FL-AAAI this year, so hopefully everyone has an enjoyable and enriching time. Thank you very much, and see you in the future.
Thank you.
Okay, thank you.
Thank you.
Thank you.
Thank you.
Thank you.
Thank you.